did something, yeah, that's it. Yeah.
Can you guys hear me now? Yeah. Online? Okay, sorry about that. I don't know what happened, but at least I'm here. I'm basically just starting to say something about the status. Swarm is doing great. All 3 satellites are doing fantastic. We just now extended the mission through 2028. Then again, we will ask for another mission extension of all 3 spacecrafts, hopefully in the end of 2028. And then we reasonably will probably not have the lower pair after that next extension. But Swarm Bravo, for now, is in good health, have consumables, and we are looking into further extensions then of Bravo beyond the ordered pair. And you can see on the plot where I put those green lines, I put the plot of the solar cycle. And it is very relevant because our hope is, of course, that we can maintain the 3 satellite constellation through solar minimum, so that we can be close to Earth while the sun is quiet and really do lithospheric measurements. Luckily, the world have changed a bit since we started planning this. We have MSS-1 now that is contributing significantly to the measurements. We will hopefully soon have MSS-2 and also NanoMaxSat by the time we get to solar minimum. So Swarm is not alone anymore when we get to that point. But clearly the 3 satellites would be very useful to have together. Nope. There we go. And that's where it's Swarm now. And I like to show this because this is why I keep talking about the lower pair going away. Basically, the red line is the altitude of Swarm Alpha and Charlie. They are plotted overlapping because they are the same altitude. You can see there are these 2 step functions between 2022 and 2024. That is our orbit race campaigns. And now the satellites are re-entering. We do not have fuel on the lower pair to lift them again. So really the sun is driving the boat right now. So that's why I said we hope we still have them for solar min. It really depends on the evolution of the solar cycle. We have a few kilos left. We can do a little bit of adjustment, but we cannot really do a proper lift anymore of the lower pair. The green line, the upper line, it's Swarm Bravo. Also there we did 2 minor orbit race campaigns, and you can see it's sinking, but much slower. But on Bravo, we have plenty of fuel left. So we have in the works and in the plans to lift Bravo again, so we can maintain it in orbit for the foreseeable future. So we have no end date to Bravo right now. Alpha and Charlie are coming down, driven by the solar cycle. So we will, of course, keep an eye on that and then see where and when we get there. So when I talk about, I'm not doing very well with this, there we go, with this change, this is a lot of text, but it's not really that relevant to read it all. I will tell you the important part of this. Every 3 years when we extend our missions, we have the ACHIO, the Advisory Board for Earth Observation, doing an assessment and coming up with recommendation, both whether or not we should extend the mission, but also what should be the goals in this extended phase. Swarm is now in the phase the mission is aging. We are approaching the end of life, at least of the lower pair. So really a big focus on what we are doing in the mission extension, in addition to, of course, utilizing the mission fully, it is to start look ahead even beyond Swarm. It is to really enhance collaborations, and we have this great collaboration with MSS. We have with CSS, NanoMaxSat, of course, when it's coming. It's a continuation in many ways on the work we are doing. So you see in yellow there I put recommendation 4, which really specifically mentions CSS and MSS. So it really shows that we are really intending to look at Swarm, not just at the 3 satellite constellation, but part of a really big international family of satellites. So this is also important here, and for the work that we will do together. We have done since the launch of MSS-1, but also the work that we will do together, both between Swarm and MSS-1, but clearly also MSS-2 when it's in orbit. No. So that's basically what I wanted to say. The summary of that slide is we are extended, we have funding for 3 more years, and really in addition to utilizing the triplets, it is really to put ourselves into this international family, which is very good. Just a little bit about the status of the instruments. This is a picture of the Swarm satellites. I put all the science instruments here, and you can see that the science instruments have gotten a new, I put it on for a while, but no, it's actually a new instrument. The Star Tracker used to be a housekeeping instrument. It's now also a science instrument. Because, let me just show you an example here. All these instruments are producing data. We have, of course, the magnetometers, which is the core of the mission. We have the plasma instruments on front, the thermal ion imager, and the Langmuir probes on front below. We have the accelerometer and the GPSR. GPSR was also not meant as a science instrument, but been used for quite a while for that. And recently, we also released new product from the star trackers, where we see that very high energy particles are penetrating the shields of the 3 star trackers on board a spacecraft. And we can basically get a high energy particle count from the instrument. And I have some examples just from that. Well, I'll do that later. This is just a little summary of something we did recently. We did the 3rd full mission reprocessing of the data. It got released right before Christmas. We put the whole reprocessed data set on the servers, and we transitioned the operational baseline to operation. We have this parallel chain over near real time or fast chain. It also very recently got transitioned into operation with this new baseline. So now we are back to having the same baseline for all our products. This is a major accomplishment. We did a few changes. Clearly, we always work on making the magnetic data better. For those of you who know DB-Sun, knows DB-Sun. The rest of you will hopefully not need to know about it. But it's really a term that helps us deal with some unwanted signals that we have in the system. And it's a constant work to make sure that we are taking care of that in a proper way. We did some rather major changes, not major changes, but some significant changes in the plasma data to get rid of some, or to flag some spikes, and also to make sure that our temperature measurements are more, temperature and density measurements are more aligned. But then also we released this new star tracker product, and I will show you, hopefully, an example of that. This is just a picture of a recent geomagnetic storm. It was in November. For those who are not space weather people, the plot, the second plot from the bottom, from the top, are showing the protons, the high energy particles coming from the sun. This storm, the line below, shows you the magnetic field of the solar wind. This was a major storm. It's not the biggest we have seen in terms of geomagnetism. I mean, it's huge, but the proton event was massive. We had a lot of very high energy proton being launched at us. I will manage. So this, Leda makes this after all our storms. This is showing the magnetic perturbation, basically the residuals from the chaos model. And you can see this is a typical storm, yet you see that during and after the storm, you get a lot of enhancements, you can say, in the polar region, and you see the depletions around the equator that last for a long, long time, typically also beyond the storm. Something I always tell or higher level people in ESA, that remember that these storms are not done when they are done. They are, they are really changing the environment around our planet for a long time also after the storms. For this storm in particular with the protons, we are now seeing the new product, the high energy particle product released from the star trackers. And you can see here, you have the, I call it the frog plot, but you have the northern hemisphere polar to the left, the southern hemisphere polar to the right, and then a view from the equator below. And you can see the South Atlantic anomaly, which you expect, but just the massive increase of high energy particle at the poles are something that we didn't really expect to see it being this massive. So it really shows that for missions that have been around for a while, we can still develop and innovate and really do new things. And this is also by getting more magnetic missions in orbit, we can do a lot more things together and really enhance the work of ourselves and each other. So then it's a slide. This slide is all dated today, and I left it like that on purpose. This was a summary also that I wrote to our director after our meeting. It was a very, very nice and successful meeting in Macau last May. And it really shows that the collaboration that we do together is really stellar. It's really an example for collaboration between CNSA and ESA, and China and Europe. So I think this is really good, the fact that we actually work together as one community. It's not just that we have agreements and exchanging data. Data is available for all. All the data is available for all, from MSS and for Swarm. The teams are working together as one team. in working on calibrating, validating the data. And also something I find very important is the data formatting, it's easy. So users in Swarm, we have spent 13 years plus developing tools, for instance, the VRES environment, and now people can import data from MSS into that environment and use the tools. And we will be very happy also to enhance this collaboration and make everything available for all in an even more streamlined way. And the last point is we are planning this RAS meeting today, and clearly the planning is done, and it looks very successful to me so far. So this is just a little bit of news also, what happened in January. The top plot I cut from a talk that Simonetta Kelly, the Director of Earth Observation, gave to member states a few days ago. And basically there was a high-level meeting between ESA and CNSA on director level, where this is the first time in more than 10 years that the highest level of those two agencies got together. There has been meetings, of course, on the higher levels, but not at director level. And it's not a new agreement, but there was a space cooperation plan that was agreed between these two agencies that has a section of electrogeomagnetism and gravity in it. And this very specifically highlights the successful collaboration between Swarm and MSS and CSS, and are really wanting to enhance this collaboration further to also include the two satellites, meaning MSS-2 and CSS-2, that we should continue and grow the collaboration. And this is now anchored at the highest level in the two agencies. So I think this is a very good news for us and for the work I think we will do. And then just a few slides. This slide, just for those who don't remember, Nils will show this a lot more. It really shows the value of working together. So this is Swarm, Alpha Charlie in blue and Bravo in red. And it shows the orbit evolution over time of those two. And clearly we are covering the pole to pole very well. Local times takes us a while. And I don't remember how long this video is, but eventually MSS will come in. And as you already know, this should not be news to anyone anymore, that MSS-1, here we go, are not covering the polar areas, but is covering local time significantly faster. So the sum of these two, or is a lot more than the sum of the part. And I know Nils is showing a lot of good examples also on why this is essential for the collaboration. So I will skip this example because you have seen it many times before. It's just an example, I say I will skip it, but then I keep talking, of just reminding you all that the Earth's magnetic field is not a constant. And I know this is the only group where I don't have to say that. Most of my talks I have to, but it's really a very dynamic thing. We are seeing these great things happening also in the South Atlantic anomaly, and clearly we care. Clearly we care because it's of scientific interest, but also because this is just an example of the single event upsets that we get on our satellites around the globe. And we can see that the environment around the South Atlantic anomaly is really brutal to any space assets that we have up there, not just to Swarm. So it's not just us, it's really the whole space community really needs to learn and know more about what's happening here. Okay. You've seen this before. And then this is my second to last slide, just to tell you that the interest in geomagnetism is not over. These are the publications for Swarm since selection. So in 2006 was the first few publications. Then it got quiet for a few years until the mission got launched in 2013. And then we see the first peak during the nominal life of the mission. And then the mission got extended. We started getting collaborations. We got platform magnetometers on board. We have the CSS and MSS coming on board. We do more ionosphere, external field, and we are seeing this enormous increase in publications the last few years. This is not the mission that is entering its last life in terms of interest. And I really hope we can keep this curve together going up and really utilize our missions together really well. So the last slide I have is really to remind you that in Swarm we have our annual data quality workshops. Since last year we have started a new tradition, and we are now joint workshops between Swarm and NanoMagSat. They are overlapping and also following one another. And clearly this is the place to discuss anything geomagnetic, I think, for the European, but also for our collaborative community. So I really hope I'll get to see many of you in Potsdam in October next year. And with that, I say thank you very much. Oh, this year. maybe any questions?
We have a couple of minutes for a quick question if there are any. You might have to. Yeah.
Yes.
Good idea.
It's great.
I'll give a microphone so the online people can hear it as well. Or I can repeat the question otherwise. Yes. Here. I can repeat the question. If you ask it, I can just repeat it.
Thanks. It's great to hear that the mission is in such good health. The instrument I was just wondering about, though, is the accelerometer on Swarm B. Do you know how good that is at the moment, or is that something that's only a bit apparent as the altitude descends?
Okay, so the comment was that it's good to hear the mission is in good shape, and the question was about the accelerometer on Swarm B, how good shape it is. And I think actually Elisabetta is in a better shape to answer that question than me. She's working more directly on this. I don't know, Elisabetta, if you want to give come up here. Yeah, just to give a quick answer on that.
Yeah. So I think the fact that the sun is active is positive for the accelerometer, because as I was mentioning to you briefly, the signal to noise ratio improves a lot during the high activity. And the plan is that, so at the moment there is a full, as you know, nominal processing of Swarm C data. They are always disseminated. Swarm A, we are actually disseminating active time. So we are starting again from 2024. And for Swarm B, we're going to disseminate all the active period, especially of storms and so this type of events. They are what they are, but the team is trying the best to still get some data out of them. But if you have a request, specific request, as I've always said, you can always ask me or Violetta, and then I can tell that to the team, and we can get the data available.
Thank you, Elisabetta.
Yeah.
Thanks for the question.
One more quick.
Yeah.
This is Alexander. Just a quick, maybe more like comment. That you mentioned that this low altitude phase will be important for lithosphere mapping, and but another thing are oceanic signals. And we know from last 2 years of CHAMP, they were really like a deal breaker in understanding that we can sense the ocean with magnetic emissions. And I think the next big boost will also in this area will also come last year's low.
Indeed, thank you very much. Just a reminder that the last part of the mission Flying Low is not just for the lithosphere, also the ocean signals will be very benefiting on that. And these are also discussions that we will have at Data Quality Workshop. We started, well, we've always done, but we started seriously last time. It is to plan the formation of the lower pier when we get down. I mean, right now they are flying with a 1.4 degree separation at the equator, and we could discuss what's the optimal separation is. We have fuel enough to do small things like that, but clearly the ocean signals are very important, and we've seen a great increase in knowledge and data publications on this in this domain the last couple of years, which we are very thankful for, of course.
I think we better move to our next speaker. So
Thank you.
let's thank Anna again.
So this is about Swarm, about MSS, and all the other satellites about Swarm Friends. First, we will look at the magnetic field during so-called close encounters, where the intersatellite distance between Swarm and MSS-1 is below 100 kilometers. The main part of my talk will be about some discussions about what we call spatial gradients and final differences. This here is a discussion meeting, and I would like to feed you with some material to encourage a discussion. And finally, some thoughts also for the discussion about the future, how we can manage, how we can orchestrate the, how we get most out of the constellation, Swarm, MSS, and other satellites. So this is the local time evolution. Anja has already shown that. We have these polar orbiting satellites, Swarm, Alpha, and Bravo, Charlie. They cover all local times within 4 months, and then we have MSS-1 covering all local times basically in 3.5 weeks, but only measuring the magnetic field between plus minus 41 degree latitude. That has impact on the data distribution. What you see here is 1 week worth of data, Swarm Bravo and MSS-1, MSS-1, of course, only at low latitudes. These are all data. So this is day-side data and night-side data. For geomagnetic field modeling, we typically select our data from night side because we want to minimize the contributions from the ionosphere. And in that week, if you only take dark data, that means sun is at least 10 degrees below the horizon, then we get this distribution. So MSS-1 only measured data in the southern hemisphere. 2 weeks later, we have this situation. Both hemispheres are sampled. Again, 2 weeks later, we have this situation. So when selecting data, particularly for MSS-1 for field modeling, it's very important to be aware of this uneven distribution of night side data and make sure that you have enough data at all latitudes to do field modeling. Let's now look at the so-called close encounters. These are when each of the 3 satellites had a distance to MSS-1 below 100 kilometers. And for each of the satellites, there are, within the last 2.5 years, there have been approximately 150 of these close encounters. And if we start with close encounters between Swarm Alpha and MSS-1, what you see here on the left side is the difference in the magnetic field intensity in F measured for these 150 close encounters. You see a slight offset, and that is also obvious if you look at the numbers there. The median is slightly positive, but the scatter is excellent. And we also, if you look at the histograms, histogram for the scalar field is more narrow. That's also expected because it's much simpler to measure the scalar field intensity. For the vector components, it's more complicated because we have to combine it with attitude. That's the likely reason why the histograms for the vector components are slightly more spread compared to the scalar field intensity. But looking at these histograms, there's excellent agreement between the scalar measurements and the vector measurements of all 4 satellites. This is now for Swarm Alpha. You can also see it for Bravo, and you can also see it make that for Charlie. So this demonstrates the excellent data quality of all these 4 missions. Let's now look at the flight direction. So I introduce now this angle epsilon. Epsilon is the angle between flight direction and east-west direction. At the equator, epsilon is equal to the orbital inclination. That means at the equator, this direction epsilon is 41 degrees for MSS-1. It's 87 degrees for M-Swarm. That means at the equator, Swarm is almost flying in north-south direction. MSS-1 is flying in between north-south and east-west. It's slightly more east-west because 41 degrees is lower than 45 degrees. Okay, that's the situation at the equator. And then you can look at what is the situation at other latitudes. And you can calculate this angle epsilon for all latitudes. If you go to a latitude of the inclination, 41 degrees for MSS-1, then MSS-1 is flying exactly in east-west direction. That's also true for Swarm. If you go to a latitude of 87 degrees, Swarm is flying exactly in east-west direction. And then you can also calculate this for all other angles, all other latitudes. That means if you look at the latitude band 30 to 41 degrees, this is this highlighted region here. Then for MSS-1, this epsilon is below 30 degrees. So it's almost east-west direction. If you go for latitudes above 36 degrees, it's even lower. It's 26 degrees. And if we now look at the distribution of the data, well, for 50% of the time, MSS data, this angle is below 31 degrees. For 20% of the time, it's below 15 degrees. So what's the impact of that? Well, let's now look at gradients and final differences. There's a big advantage of using gradient data for geomagnetic field modeling, because the large-scale field, in particular the dynamics of the magnetospheric field, is heavily reduced. Okay, now the difference between finer differences instead of gradients. What is measured by Swarm and MSS-1 and all other magnetic satellites is magnetic field. This has units of nanotesla. And a gradient would have units of nanotesla per meter. Think of ESA's GOCHA mission. GOCHA measured in situ the gravity gradient. So these data, the GOCHA data, have units of acceleration, which is meter per second squared, divided by meter. But for magnetic field measures, but for magnetic field satellites, we measure the magnetic field, so units of nanotesla. We take finer differences, but we often call them gradients. It's not correct. These are not gradients. So what's the impact of that? We use the so-called long track finer differences of near polar satellites. We call them often north-south gradients, but they are neither gradients nor in north-south direction. They are almost in north-south direction. If you go closer to the poles, at a latitude of 87 degrees, Swarm is flying in east-west direction. So it's not at all in north-south. And for MSS-1, well, we call them often east-west gradients. They are neither gradients nor east-west direction. Only at latitudes of 41 degrees, it is in true east-west direction. So what does it mean? Well, we have a true east-west differences. That is possible if we take the difference between Alpha and Charlie when they are at exactly the same latitude. That's a true east-west differences. Okay, if we now look at how do we use these data in chaos. We use a long track finer differences with a sampling rate of a distance of 15 seconds, corresponding to a long track separation of 115 kilometers. We do that for each of the individual satellites, Swarm Alpha, Bravo Charlie, MSS-1, Champ, and so on. And then we also take the east-west differences between Swarm and Alpha and Charlie when they are at exactly the same latitude. That means a slight time shift of one of the satellites, typically up to 10 seconds, in order to make sure that they are exactly the same latitude. Okay, let's now look at the data here. What you see here are the residuals in the latitude band 30 to 41 degree for Swarm in the top, for MSS-1 in the middle, and for the difference in between Alpha and Charlie in the bottom. Okay, and this is now a time series. We can also look at the histogram. The histogram is shown here. On the left-hand side, it's north-south based on Swarm. In the middle is east-west based on MSS-1. These histograms are very similar. And then we have the true east-west difference based on the difference between Alpha and Charlie. The spread of this histogram is larger, but that's also understandable because for the long track differences, so the left and the middle figure, we are taking differences of data from the same instrument. So any bias, slight bias in the calibration will cancel out. Here we are looking at the difference between measurements taken by different satellites, different instruments, and so on. Still, we have this excellent agreement here. Again, a documentation of the excellent data quality. That's for night side data. For the day side data, it's slightly more spread. It's also expected because we have ionospheric contributions between the two satellites there. Okay, that was now about Swarm and MSS-1, but we also have these other satellites. We have platform magnetometer data from cryosat and from Grace follow on, and we have scalar data from CSS. Here you see how they sample the magnetic field at different local times. So we have a really good sampling in local time, and that can be used to separate the different contributions. This is work done by Alexander Graver. It's the storm of January. What you see here is the vertical magnetic field at ground based on a combined analysis of all the satellite data and ground-based data. Okay, now finally, let's look at modeling of the lithospheric magnetic field. What is needed for that is very low altitude data, below 300 kilometers. And presently, the main source for lithospheric field modeling is CHAMP. It's the last 2 years of CHAMP at altitudes below 350 kilometers during extremely quiet conditions. As an example, this LCS-1 model is based entirely on final difference data. And now we are waiting for additional low altitude data during geomagnetic quiet conditions. So expected for 2030 and perhaps 31. So what's now the contribution from the different satellites? If you look at Alpha and Charlie, they will measure east-west differences at all latitudes, and hopefully they will still be in orbit when we have the when we get to the next solar minimum. You should also remember that the role of Swarm has slightly changed for lithospheric field modeling because we now have all these other satellites. Then, well, we hope we will get soon successful launch of MSS-2. MSS-2 will measure the magnetic field at very low altitudes of 200 kilometers. That has never been done before. Nobody has yet measured the magnetic field at an altitude of 200 kilometers. We don't know whether it's, for instance, whether it would be possible to make vector measurements at these low altitudes, because there might be turbulence, there might be a shaking of the satellite, which makes it not possible to measure altitude. In that case, we hopefully still can measure the magnetic field intensity, F. I would then argue, well, this is good, try to go even lower. Each 10-kilometer in altitude counts for lithospheric field modeling. Even if we only can measure the magnetic field intensity, it's worth to go even lower. We will have problems when we only have the magnetic field intensity near the equator. We will have disturbance by the Backus effect. But there, perhaps MSS-1 can help. If we lower the altitude, if the altitude of MSS-1 is lowered such that MSS-1 can make vector measurement at low latitudes and low altitudes, that could compensate for a possible Backus effect when we only use scalar data from MSS-2. So finally, let's look at the model resolution matrix of LCS-1. You can see the main contribution is still from CHAMP. We have a little contribution from Swarm because we are at altitude is too high. On the left bottom, you see the contribution of model regularization. So the high degree terms are mainly determined by model regularization. There, we hope that MSS-2 will help. Yes, here this is in the future. Well, that's the present situation of the altitudes. MSS-1 has still enough fuel, so perhaps we want to continue in that way in order to have a really long mission. We also will have MSS-2 and nanomaxer, of course, but we also could consider, or should be considered, instead of keeping this MSS-1 at a long mission, to go down and help for lithospheric field modeling. So there is this trade-off between lithospheric field and core field measurement. Thank you.
Yes. Do we have a question?
MS2, low altitude. You said no attitude error. Do you mean absolute no attitude data, or maybe great?
Well, and we don't know what happens. I'm working with the worst case scenario, no attitude data. It's shaking like hell. So. But I know what you are thinking of.
Gotcha.
I was just wondering, MS2 is supposed to be on an island.
Yes, yes, yeah.
But what is the current situation with collision avoidance? If you get a satellite, most of these highly elliptical orbits, they never go down that much, precisely because there's a lot of stuff and a lot of LEO satellites. So I was just wondering, has this been altered, and is there a simple answer?
We have discussed the perigee is around 200 kilometers, but altitude should be less than 2,000 kilometers. Altitude is 600 kilometers. So not too far away. Originally, we put around 5,000 kilometers, but now we reduce that to 1,600 kilometers. As year, actually, the past is not that useful to extend to 5,000 kilometers. That's average.
That I understand, but my main question is, if you go down, you're basically crossing the street you're crossing the street at which lowest. And so how do you deal with collision avoidance? I don't know, I'm just out of curious, because that's one thing that I think is becoming more and more concerned. In many constellations are about to avoid precisely between 200 and 5,000. So you're flying in collision protection.
Yeah, I understand. Because that's different plans so far, that's possibility you think about avoid 230. So we haven't decided the exact obviously should be the perigee is around 200 around.
I will thank our speaker again. We'll move on. Thank you, Niels.
Okay, thank you. Thank you for the invitation. So today I'm going to talk about the NanoMaxSat mission. So just a quick introduction to this mission. It's an ESA Scout mission, and I think it's important to stress a few things about this. Number one, it's not run like an Earth Explorer, like Swarm. ESA requests a consortium to be built, and this consortium is next in charge of building the satellite, running the satellite, and distributing the data. So this is run entirely by the consortium, but of course with strict ESA checks. And the data will be freely available, as is generally the rule of ESA. The other thing is that this is a constellation with which we are building with 35 million euros, so it's a much lower cost than Swarm. So there are a number of challenges in this respect. So the consortium that we put together is basically illustrated here with the logos, and these are the people who will actually run the mission. But we also have, is that working? Yes. Science advisory group. So a number of you perhaps are on the list. And this is extremely useful because that helps us providing guidance, especially that we keep on having back and forth discussions about what is possible, not possible, and what are the requirements, so that we need to have this support from the science community to avoid our industrial partners or ESA to be tempted to relax some of our requirements in a way that would not be too good. So thanks a lot, by the way, to the SAG for assisting us in all that matter. So the mission itself is obviously connected to Swarm, MSS, CSS, etc. And we are obviously looking into the Earth's magnetic fields. There are a number of differences that I want to highlight. These here are the usual targets that we've been discussing already. And so that the point here is the targets are similar to those we've seen. What is different is that we want to capitalize on the low inclined orbits, just as has been discussed. Both Niels and Anya showed that 41 degrees covers the local time very fast. And as Niels pointed out, if you have only one inclined satellite, you either have the, half southern hemisphere or the northern or the southern hemisphere. And if you have two satellites, that you can manage to cover everything, and I'll show this in a second. So the point here is the progress we want to make is by the constellation design. The payload, the rest in terms of measurements is very similar to what we have on Swarm. And that's where we want to expect to be able to contribute to make progress, especially on fast core signals and things like that, because we cover the local times faster. Now, the other aspect of the mission is that we also want to look into the ionospheric environment, and this is a bit different from, actually all missions are a bit different in this respect, because MSS is also a bit different in this respect with respect to Swarm or CSES. And in our case, the idea is we want to have some instruments to look into small scales in the ionosphere, and this is done by having high-frequency magnetic field measurements and also high-frequency measurements of the electron density, and plus a number of tools that we can use, such as the fact that we can have access to waves that propagate within the ionosphere, and these waves are affected by the ionosphere, so they provide some extra information. This is something that we can only partially do with Swarm for the time being. That can be done with CSES to some extent, so each mission has a bit of its peculiarity. And here, the point is that we innovate a little bit in terms of instrumentation. So compared to Swarm, we have a slightly different orbit configuration to improve the local time coverage, and we have different instruments to also look into high-frequency stuff and more details in the ionosphere. So the design hasn't changed since the very beginning. The idea is that we have this polar orbit, which we want to be similar to Swarm, because of course, in terms of inclination, we hope, by the way, we don't have propulsion. We have gravitationally stabilized satellites. And so we want the polar orbit to be, useful in combination with Swarm, especially Swarm Bravo, if, Alpha and Charlie, if they're still around, of course. And the two inclined orbits, the important point is that we want to phase them 90 degrees in terms of right ascending node. That basically means that you shift it by to cover the local times nicely, as I'm going to show later on. The instruments is basically, I'll come back to these in more detail, but we have an absolute magnetometer that will actually provide the vector magnetometer, the vector field. So it's a self-calibrated instrument with star trackers at the tip of the boom, and that will provide the 1 Hertz vector data, very similar to what we have with Swarm. And then it will also provide 2 kilohertz scalar data, which will be complemented by a vector magnetometer, which is a mid-boom, also 2 kilohertz. And on Swarm, we only have 50 hertz vector magnetometry. So the idea is to have access to higher frequency. And then the multi-needle Langley probe is, and the idea is that I'll show this later on, is that we can access high frequency as well, 2 kilohertz, while still getting 1 hertz, especially for the electron temperature. And then something that we have also are dual GNSS receivers with 3 antennas, and this will allow us to do some radio occultation. And it turns out that the 60-degree inclination is very nice for that type of investigations, I'll show in a second. Okay, so these are the requirements. I'm not going to go through these, but that has been worked out with the Science Advisory Group and tried to make the best, of course, of the instruments, the payload, and that drove the design of the satellite. And this is a big challenge, as you always know. We don't want a satellite to produce perturbations, so the entire satellite has been designed to avoid this. The orbits, I'm going to show this. Been showing this quite a number of times. Contrary to what Niels was showing here, I'm splitting the maps in terms of local time covered. So that's 1 day. And if you have a map, for instance, the one on the top left, is local time between 0 and 3 in the morning. And so you start filling as the day passes. And after 10 days, you cover this. So blue is the polar orbit, green and red are the inclined orbits. And as you can see, they nicely cover the portion that the other inclined orbit is not covering. So that after essentially 30 days, you've been covering the entire latitudes between -60 and 60. And that's the whole point that we would next use this for typically. So that's 40 days. And that's very useful for trying to recover fast signals. So that's an early simulation that had been done, just illustrating the fact that if we start putting fast signals in the core and try to recover them with this constellation. So on the top left is what you expect. I mean, the initial signal, that's the extra signal on top of a chaos model and all of the sources. We try to see if we can manage to recover it. On the right-hand side is what we recover, and the residuals is below. And this is a simulation over 3 years. So obviously, at the beginning of the mission, we're not very good. But if I'm good at starting this, can I start this? Yes. You will see that it does not want to run. Or does it? How do I do? Oh, there you go. Okay, so we recover nicely now once we're in the middle of the mission. As you can see, the two top maps and the residuals are small, and then it becomes not as good later on. Then the nominal lifetime of the mission with respect to ESA is 3 years, but I recall, just remind you that Swarm had a nominal lifetime of 4 years. So hopefully we won't be able to last 10 years, but we expect to last at least 5 years. Oh, now it wants to run. Okay. This is an illustration about the advantage of the inclined orbit for radio occultation. And the main point, so this is basically showing a number of traces where we can collect radio occultation profiles very near the satellite, because that's what you're most interested in. I don't have much time to discuss what radio occultation is about, but it more or less allows you to scan the electron content along the ionosphere through the rays up to the GNSS. But if you have nice configuration, you basically do this close to the satellite as you go down in terms of altitude. And the configuration is very nice because the GNSS satellites, they basically are 55 degrees, 56 degrees in terms of inclination. And it's nice to have a similar inclination in this respect. So we've witnessed this. It really is a nice configuration for this as well. I mentioned high frequency signals, and here I'd like to, oh, by the way, one thing I should mention, Anya said that there has been a recent release of an update, a new version of all the data. We've just released the burst data from Swarm in the latest version as well, consistent with the update that has been made. And the reason I'm mentioning this is that these burst data that allow us to detect signals that we call whistlers. They're produced by lightning. And the point is that when you get those lightning, they produce a kind of a peak that propagates in the ionosphere, and then they get dispersed, and you get this characteristic signal of a dispersion. And this provides some information about the electron content along the path. The interesting thing about this is that it allows to have some information below the satellites. GNSS always provide you with information above, or possibly scanning using radio occultation, but you rarely get information from below because you're not looking downwards. So this is an opportunity to also get some information about the ionosphere below the satellites. Okay. In the case of NanoMaxSat, the point is that we want to capitalize on what we've seen with Swarm, but now that's why we have 2 kilohertz signals rather than 250 hertz on Swarm. So that allows to see a lot more. And the whistlers, by the way, are not only the only signals at these frequencies. So there's a whole area of interest for waves propagating in the ionosphere with NanoMaxSat as well. I mentioned the fact that we would have the Langmuir probe working at high frequency, 2 kilohertz. So if we have the combination of the vector field, and so that allows us to scan field aligned currents, for instance, at a very fine scale, plus the electron density as well. So that the idea is to access scales that we currently do not access. They've been accessed through Langmuir probes on a number of satellites, sounding rockets, etc. But this was never done with a magnetometer working simultaneously. So there's an interesting opportunity here as well. So I tried to finish. I don't know how long I've been, but with the magnetometry payload. So coming back to the status of the mission right now. So we're in phase B, and the hardware is always very advanced. So the instruments do exist in various versions, like engineering units and stuff like that. So here, just this is showing so NanoMax deployed. And the picture you see is describing the boom that is folded with the optical bench, and you get the star trackers and the MAM, which is the absolute magnetometer, providing also the vector field at 1 Hertz. And everything is compact because it's 16 new satellites, so it's quite small. It's roughly 20 by 20 by 40, a little more centimeters. And it's roughly 30 kilogram, 35 kilogram. And there has been a lot of developments specific for NanoMax, starting with the boom, but also for the star trackers. There are deployable baffles that have been designed by DTU, and of course some progress in miniaturization for the various instruments. On the multi-needle Langmuir probe, so this one has been run on various missions in the past, but the characteristics here is that we want to run it in a okay, I don't know how familiar you are with the Langmuir probe, but the idea is that you have probes, you have voltage you impose the voltage, and then you capture some currents. And there are the various ways. Either you have a single needle and then you sweep the voltage and you see how the current is responding, but that takes time, which is why standard Langmuir probes usually are 1 Hertz or a few Hertz. But here the idea is that if you have several Langmuir probes acquiring simultaneously at fixed voltage, then you can reconstruct at higher frequency. But the idea is we want to run 3 of them in this way and 1 the standard way, so we can also access electron temperature. So that's a new way of doing things. And here you can also see the GNSS antenna. There are 2 of them at the front and RAM and aft, and for the radio occultation, and there's 1 on top for tech and precise orbit determination as well. That's the boom again, because this was, so it's a 3-meter boom, compact into 20 centimeters when it's folded. So you can see it partly deployed with the optical bench. And on that picture, you don't see the instruments, it's just the boom itself. And of course, you'll have to deal with all the harness and stuff like that. So it's quite a challenge, but it works, at least on the ground for the time being. And this is the overall mission architecture, the way we will operate the mission. So the idea is that they will be launched, and that's Open Cosmos, the company we're working with, building the satellites and operating the launch, managing the launch, then operating the space segment and the ground segment. They basically have the connections with the communication with the satellites. They collect the data, then it is sent to us within IPGP, where we'll process it into the standard level. Well, in the ESA language, normal language, it's called level 1 and level 2, where we now have level 1A, level 1B for Swarm, etc. But that's the whole idea. And there's the role also of the science advisory group. And then the idea is also to capitalize on the science community to actually get higher level products, including the disk. That's the status, that's where we are. So the idea is that we will launch in 2027. Right now, we're working on having the launches secured, etc. But the target is to launch actually possibly mid-2027 for the first satellite, because that would be the polar satellite. And Anya mentioned that we will have a workshop in Potsdam, so that's correct. It's Potsdam, by the way, not Postdam. And I guess this is, I just want to mention, so that's NanoMax. Niels mentioned what would go beyond, but one thing we're working on with with OpenCosmos and a number of things, is that we want also to work on the possibilities for collecting efforts from other countries who right now have not necessarily developed space missions could contribute to these type of nanosatellite, which are much cheaper, because an individual satellite now the cost is roughly 5 million euro. So we're trying to figure out how we could possibly expand the constellation in a collaborative way, a little bit like we run the intermagnet observatories. And that's it, I think. Thank you. Yes.
Do we have one question for Gautier? Kathy?
Yes, Gautier, you talked about the standard level products from ESA, but would that necessarily fast data or something equivalent to near real-time data?
No, that we cannot afford. It would be fast as it used to be fast with Swarm before we introduced the fast data in Swarm. No, the latency is expected to be, we're working on the latency, which is on the order of a week or 2 weeks, basically because we cannot afford to maintain a team through the weekend, et cetera, et cetera. So, unless ESA decides to give more money all of a sudden.
Okay, thank you, Gautier.
Thank you.
Well, thank you so much for an opportunity to be back here. I was here a couple of years ago at the MSS conference and thinking, wouldn't it be amazing to come back and talk to you all about our own mission. And here we are 2 weeks from launch and I get a chance to chat about it. So yeah, thank you so much for the opportunity. So I'll go back. So a quick introduction. I'm the founder of IOTA Technology. We're a small company based in Oxford. And for the last 5 years now, I've been working on a 4U CubeSat to capture data in support of the World Magnetic Model. So we are part of the MagQuest program. So this is an open innovation challenge from the US NGA. And the idea is to support new ways of data collection in support of the World Magnetic Model. So agnostic as the methodology, this could be ground-based systems, it could be space-based systems. And this program started in 2019. We joined it about 6 months later. And that was in phase 2, and we're now at phase 4. So we've gone down from about 200 organizations to a remaining 3 teams who are left, ourselves, University of Colorado, and Spire. And we're all producing CubeSats with very different instruments, very different designs, and we're all launching on the same mission, so all eggs in one basket on Transporter 16. So NGA have offered us not just the funding to do this, but also technical support. So that's included a range of experts and facilities over at NASA Goddard, and they've really helped us kind of to get towards this point. And we are at 15 days, 22 hours, and 49 minutes to launch. Not that I'm counting. So this is IO1, and you'll see there are a lot of similarities between our mission and the ones we've spoken about so far. We have a scalar magnetometer like Swarm and other satellites. We have 2 star trackers. We have a vector magnetometer, and we have a deployable boom. So we're launching to 590 kilometers. Hopefully, we're going to stay there for about 3 years. We're in the sun-synchronous polar orbit. That's ideal for World Magnetic Model data collection. And we're aiming to achieve an accuracy target of less than 5 nanotesla. But really, the critical difference between what we're doing and these other missions is that we're absolutely tiny. So this is the kind of the family of satellites. I'm sorry, MSS-1 is not on here, but I seem to remember it's about a similar size to Swarm. Got 9 meters for Swarm, getting down to 3 meters for NanoMagSat, and then the absolute baby of the family at just under 1.3 meters is IO1. So for context, you know, where our payload can almost fit inside one of the star tracker baffles for Swarm. It's that small. So when you get to this point, really everything is miniaturized. So all our instruments, all our components, we're talking kind of thumbnail-sized instruments, and we're really kind of thinking about every single milliwatt of power going into these. So everything is optimized for space and for power consumption, and also for cost. Obviously, there are a lot of different challenges. We're trying to shrink everything down to this size. I can't mention them all here. But the 3 ones I think that we've come across that have been most challenging, the first one's magnetic contamination. You know, CubeSats are fundamentally modular. There are a lot of different modular subsystems. those subsystems are not designed to be particularly magnetically clean, and we don't have a huge amount of choice about what subsystems to use. So it's an important first step is to understand what we're using. The second one is measurement stability. We just don't have access to some of these fantastic instruments that are used in these other missions, these very kind of stable, large, quite power-hungry atomic magnetometers and that kind of thing. And the third is attitude knowledge. There's no sense in having the best vector mag in the world if we don't actually know where that vector mag is pointing. So let's talk about the first one. And the quick win for magnetic contamination is to have a deployable boom. So this is the boom made for us by Oxford Space Systems. If it looks a bit like a spring, it's because it is in some ways. But unlike a spring, when it deploys into a fully rigid state. So one of the first things we did was approach Oxford Space Systems, with this request to transform one of their helical antenna elements into a boom. Before doing this, we really had to understand how long this boom should be. Too long and we lose attitude control of the satellite. Too small and we run into magnetic contamination issues. So really at the very beginning of the process, the first step is to go to our partners, and Clyde Space up in Glasgow are manufacturing the satellite bus for us to try to understand how magnetic these CubeSat subsystems really are. And there's very little data available on this. We went through every single subsystem, from the batteries to the onboard computer and the radio, and we screened it to try to understand what the magnetic moments are. And we were pleasantly surprised. When we put together this synthetic model, we noticed actually that, certainly from a static dipole point of view, the disturbances are fairly small. And actually at location of our scalar mag, we're looking at less than a nanotesla of overall disturbance, which is what we were aiming for. Of course, static disturbance is really only half the battle, maybe it's 25% of the battle. The remaining big challenge, of course, are dynamic disturbances. And we have two instruments on board the satellites that produce those. The first one are reaction wheels. So unlike larger missions like NanoMagSat, which rely on gravity gradient stabilization, I believe, we can't do that. We're simply too small. So we have to rely on active attitude control. So we have reaction wheels, and of course, reaction wheels containing neodymium magnets, the worst offenders for magnetic contamination. So we had looked to see what kind of disturbance these produce. And the fortunate thing is, because these wheels are so tiny, at 23 centimeters, we're looking at about 20 nanotesla peak-to-peak disturbance. And the good news is we're not at 23 centimeters. This boom extends us, so we're more than a meter away from these instruments. And the amount of disturbance from reaction wheels is about 0.1 nanotesla peak to peak. And that fits safely within our error budget for this mission. The next one is magnetorquers. Obviously, we need to desaturate those reaction wheels. The way to do that is with torquers. Obviously, at a magnetometer location, those torquers, because they're effectively electromagnets, are going to produce quite a big disturbance. The way to calibrate that out on our mission is that we're turning off the torquers for 100 milliseconds of each 1 second period. And we're attempting to characterize the square wave that is produced. To do that, we have to run our instruments fairly fast. So even though our overall requirement is 1 hertz for this mission, we have to capture data at least 40 hertz in order to fully capture these square waves and basically kind of dynamically calibrate our magnetorquer disturbance every single second. So we've been able to test all these assumptions at NASA Goddard, which has been an amazing opportunity to go to this fantastic facility. If you're familiar with the Goddard Space Flight Center, they have this giant 40-foot Helmholtz coil. It's the one they use to test the Apollo rovers in for magnetic contamination. It is just split over 2 stories. It's an amazing place. And it allows us to produce any magnetic fields in any direction in a very clean environment and really understand everything that's going on with the satellite magnetically. So that has been absolutely invaluable to have their support there. You can see that's our flight model there with the boom extended and then in the stowed state. So instrument stability, that's probably one of the most important things. We have a fluxgate magnetometer on board. This is manufactured for us by Bartington Instruments. It wasn't actually our first choice. Originally, we were intending to go with a PNI magnetoinductive sensor, but we realized quite quickly that trying to run it at 40 hertz isn't possible to get the kind of precision we need to really characterize that magnetorquer disturbance. So after spending a few years kind of comparing our various solutions with the kind of fluxgate at state of the art and saying, oh, we can do better than this, we can make it smaller or cheaper, actually fluxgates are awesome. So we've asked Bartington Instruments to create this fluxgate for us. which is a rod core flux gate. And it is incredibly small. There should be a scale here, but this is, it's about 15 millimeters high by 15 by 15. My thumb is at the top there. Absolutely tiny, but it's still a relative instrument. This will still drift over the course of the mission. We need to maintain accuracy over about 5 years. And the way to do that is, of course, with atomic instruments. Now, there really are only a few companies in the world that create atomic magnetometers at that kind of scale. One of them is Twin Leaf, based over in the US. We went to them with kind of an impossible proposition. We wanted an atomic magnetometer that consumed less than a watt of power, was around the size of my thumb, and drifted by less than a nanotesla over the course of 4 years. So an extremely challenging brief for them. And a few years later, especially since Twin Leaf, they haven't made instruments for space before. So we've teamed up also with RailSpace to test this. And over the course of the last 2 years, we've come up with an instrument you see here. So it's the one kind of wrapped in MLI you see there, just kind of under the circular lid. That's the instrument here. So it's a pulsed-free induction decay magnetometer. We are shining a laser through a very tiny vial of cesium atoms. We're applying a DC magnetic pulse, and we're watching the precession of those atoms with a photodiode. So it gives us a really clean idea of what the magnitude of the magnetic field is in a very, very tiny package. And I believe it will be the smallest atomic magnetometer ever flown in space. So that's going to be an exciting world first, I think. So next up is attitude determination. Like I said before, there's no point having a great vector mag if you don't know which way it's pointing. Originally, our idea actually was to put our star trackers in the body of the satellite here. We had a very complicated idea involving bouncing a laser, this red line here, off the bottom of our payload, off a mirror, very similar to what MagSat did in the 1960s. That way you can determine how the angle of your payload shifts, kind of a laser optical bench, if you will. Of course, that works well in 2 axes of rotation, but if your payload kind of rotates around the long axis of the spacecraft, you can't pick that up. You can get around it with polarized light and quarter wave plates, and eventually realized we were turning a magnetometry problem into an optical problem, and the whole thing became incredibly complicated, too complicated to pursue. Luckily, we came across ArcSec. So ArcSec produce, again, it's all about the smallest in the world. So they produce the smallest star trackers in the world, these absolutely tiny matchbox-sized instruments that can give you attitude solutions to an accuracy of about 10 arcseconds or less. We need 2 of those, and we were able to work with them for a couple of years to make these non-magnetic. That was the first thing. And also design very, very tiny baffles you can see here, and that's all fit into the kind of gondola we have at the top there. So, the star trackers are non-magnetic, but they're not perfectly non-magnetic. They still contain, currents are flowing through them. We have to separate them from a vector magnetometer in some way. Those of you familiar with Swarm know that the optical bench there is made from some very exotic materials. We also tried to go down the exotic material route. We started off with ceramics, so machinable ceramics like Maycore and Shapel, and attempting to find something that matched the CTE of aluminium. And there's a horrible feeling when you're kind of bolting a ceramic part to an aluminium piece and you hear this very high-pitched dink sound as a crack propagates across your incredibly expensive prototype. So ultimately, we decided to move away from ceramics for that reason, and we moved on to composites. So at the moment, we're using a really interesting peak carbon fiber composite material for this. There's a few reasons for this. One of the reasons is that it's slightly conductive, so it helps us kind of dissipate any static charge buildup. Any charge buildup. And it's also extremely lightweight. It's a bit thermally conductive, so some of the heat from our star trackers is conducted down into the vector mag to keep it at a reasonable temperature. It's very lightweight, it's very rigid, and it matches the CTE of aluminium. We can play around and kind of tune it to match the rest of our components. Okay, so where are we now? This is us taking the satellite all the way to the US. I should mention actually the fourth challenge with CubeSat design for magnetometry is to actually getting it to the launch pad in the first place without upsetting your delicate calibration. So a lot of time sitting with security at Heathrow, trying to persuade them not to put it through an X-ray machine with magnets in the conveyor belt. That slowed us down for a bit. And then trying to get it into an economy seat with a ridiculous number of seat belts to avoid turbulence causing it to hit the ceiling. So we got there, and it is launching in 2 weeks at a I mean, the LTAN is 2 o'clock in the morning, so it's a really awkward time for us to go out there and watch it. It's in the middle of the night. But for you guys, it'll be about 11:30 in the morning on Sunday. So 15 days, 22 hours, and 34 minutes left to launch. Thank you so much.
Do we have any questions?
Sure. Yeah.
Sorry, if I'll just repeat
on,
the question,
that's fine.
because, apologies for people online, I forgot to do that earlier. So the question was, what's the cost?
Good question. We can manufacture the satellites for just over $1 million. So if you want to do a replacement mission, that would be an interesting possibility. And we would love to make replacement missions. You know, one of the nice things about this design, it has an incredibly high ballistic coefficient. So we can remain in orbit, certainly at 590 kilometers almost indefinitely. We could launch to VLEO if we wanted to and get a reasonable amount of time collecting data despite our small mass. So we would love to remanufacture this. If any of you have missions you would like to get us involved in, let us know. Thank you.
Kathy had a question.
Hi.
The question is, what do you lose from having 2 star trackers instead of the quite common 3?
Redundancy is a big one. We definitely need both trackers to continue to operate. We get 100% availability with 2. We don't know. We should always get, we did some analysis and worked out with 3, because of the way we have very strict attitude control, we're effectively always nadir zenith pointing. So our 2 star trackers are always pointing towards zenith. Having a 3rd tracker wouldn't make too much of a difference to us.
Thank you, Hugo.
No worries. Thank you.
Hey, good morning, everybody. So we've had a load of talks about the measurement of the magnetic field and the missions and the great science that goes on behind it. But realistically, society just wants one thing from us, which is a nice magnetic field map. And the rest is just detail as far as them. But it's nice that they fund such great instruments to do that. So how do we contribute to society, I suppose, is what I'm going to talk about here. And of course, this is to big magnetic field models, such as the International Geomagnetic Reference Field or the World Magnetic Model. And they are big international collaboration efforts. And I was lucky enough to lead the last one, which is the IGF-14. So this is myself and Clemens' work, and then all the work from all the evaluation panel, and all the people in this room have at some level contributed to this model. So thank you very much. Okay, so yeah, the majority of the human race don't care about the magnetic field. In fact, probably don't even know it exists, but they do use it inherently every day of their lives without realizing. And of course, originally the magnetic field was measured and tried to be understood for navigation purposes, and it still is today, with declination being the angle between true north and magnetic north. And because all maps are usually aligned to true north, then you need a correction to understand the direction that you're pointing in relative to the compass direction at your location. So in the olden days, that was literally a compass, and of course ship's compasses were vital. But nowadays, everyone's got a smartphone, and even people who don't know about magnetic fields use it when they're looking for their Pokemon characters in their virtual reality landscape. So with that, just as a background, people have been trying to understand the magnetic field for certainly hundreds of years, maybe even longer. And one of the earliest attempts was by Halley, who spent 2 years tracking around the Atlantic Ocean, measuring the declination angle to make this map, which is the first map of the magnetic field that we know of. And I think there's a copy upstairs, actually, if we were to go ask the librarian, they could probably dig it out for us. This is also one of the first maps to use contours to show that the lines of equal value across a spatial area. And of course, during the trip, Halley realized that actually the magnetic field was changing constantly and in a non-linear way. So he realized that actually the maps would not be useful for determining longitude, which was his original purpose. If you jump forward a few hundred years, we've got a plot on the right-hand side there showing the declination change over the last 120 years or so, as measured in the UK, starting in the Greenwich Observatory, which is a few miles up the river here, and then being picked up by the other observatories, Hartland, Estelmere, and Lerwick, which were established because London became too magnetically noisy. But you can see there that the rate of variation is constantly changing, up and down, and it's not at the moment possible to predict it. So therefore we must measure it and make maps of that to continue. And we were talking yesterday in our workshop about jerks, and the famous 1969 jerk is there very, very evidently. And then there's been some smaller variations as we get better and better measurements in the last decades. Okay, so the International Geomagnetic Reference Field is then a large-scale map, a global effort to try and make something that is useful for the public and to justify our salaries most of the time. So it's a very formal process. It's created under the auspices of the International Association for Geomagnetism and Aeronomy, and that itself is part of the International Union of Geophysics and Geodesy, or Geodesy and Geophysics. And then that itself is part of UNESCO. So it's all flows down from the UN and has that sort of very formal UN feel to it, with committees and workforces and tasks and all that. So in the last iteration, the 14th generation, there have been 13 before that. It was originally started back in the 1960s as a collaboration between some of our more famous forefathers. And over the years, it's been updated every 5 or 10 years, within between 2003, for example, was an update because we had better satellite data. So it's sort of settled on a 5-year update schedule, but can change. It's not set in stone. The idea is that forms a committee, myself and Clemens, and then we sort of establish the ordering in which we ask for teams to form. We ask for volunteers for an evaluation panel. We ask everybody to contribute by October of the previous 5-year endpoint, and then we release the model in December of that year, and this is 2024. And it's represented as spherical harmonic fields up to the green order 13, and here's some of the coefficients just in that table on the right. And we ask for two main field models in 2020, 2025, and then a prediction for the next 5 years to 2030. And then when it's released in January, it's valid for 5 full years. And in this last iteration, we now have included Swarm and MSS data using nearly all the models, and then one model had CSS data in it as well. So it's now a global international effort, and all the satellites we have, and we will have in future, hopefully, will contribute to making this. Okay, so this was a record year. We had 19 teams this year. We had 47 different candidates, and we had a record number of researchers involved, so 85 or roughly 85 as last count. The table shows you a little X where somebody's contributed a model and a dash where they didn't contribute a model. So most teams contributed to most of the 2020 model, which is the DGRF, the 2025 model, which is the IGRF, and then the secular variation. Now, with that number of models, in the past, it was all done by email, and so you'd have V1, V2, and so on in your inbox, and there would be a lot of going back and forward, and quite easy to sort of make mistakes or get the wrong model. So with the help of Ashley Smith and Clemens, we set up what's known as a GitHub repository, which is an online method of collecting data and running code automatically. And in this case, we set it up to generate comparisons between the models relatively easily. The idea is it's open access. Anybody can go away and recreate this, and it's part of the FAIR principles, which is findable, accessible, interoperable, and reproducible, or something like that, or something that goes like that. And everybody's free to go and look at the GitHub repository, download the evaluation themselves, and run it to their own heart's content. So this is what the GitHub repository looked like, and what we asked the teams was to upload their model to the GitHub repository, and then they can then do an automated comparison to all the other models, or they can download the repository, run it on their own computer, check their model works okay, and then upload it separately. Or people could email it to me if they really wanted to, and then I would do that for them. So we created this automatic website. Ashley set up a lovely job. So you could go to this iaga-vmod github.io, and you could see the models being submitted and then updated more or less in real time as they went along. So that was a really nice innovation. It meant that it took away a lot of the work that was required later on for comparisons. So this is something like the plots that were generated. There are some standard ways of checking these things. You look at the root mean square differences between the models and so on, and you can plot them out as a sort of a square or a half square triangle plot showing the differences between the models. So for example, the BGS model was 10.7 nanotesla root mean square difference with CSS, and a little bit less 5 with DTU, and so on and so forth. So that was a kind of quick visual comparison. And then you could look in detail spatial maps to show how the different models were different from each other. And this is a comparison between the median of all those candidates and each individual candidate. You can see some have different structures and some have very little structure. Normally there's some sort of hemispherical bias that appears. So this allowed the task force who were doing the evaluation to understand which models were different and why, and whether that was a problem or not. So the IGF candidates, you can see that, again, they're quite similar to each other. One candidate stood out because it wasn't made using satellite data, it was made using observatory data. That's the Strasbourg model, and that's why it tends to look a little bit different. And again, another way of looking at the model differences are via these triangle plots of coefficients. So this is just how different each coefficient is from each other. And sometimes you can see that there's some structure along the order 0, which would be a zonal difference, or there might be structure along, for example, the sectorial terms. And or in the case of the Strasbourg model, all the terms are quite different from the consensus models, which are all built out of satellite data in the other cases. Okay, so the task force had time to go away and look at all the different models, apply their own tests if they wished, and then at the end we had just a democratic vote. So what was your favorite way to combine things? So with the DGRF, all the models were very, very close to each other. There really wasn't much difference between them. So we voted to take the median of all the candidate coefficients just because it's an easy thing to compute. In the other two cases, the models were more spread, the differences were larger between them, so we opted to do what was called a Huber-weighted mean in space, which is where you effectively turn all of the models into spatial maps, and then you sort of effectively weight them in Huber space spatially, and then you convert it all back to spherical harmonics. And that way everybody's model contributes in some meaningful manner to the overall final model. Then it was released on the NOAA webpage, and Ashley also set up a Zenoda repository, which is the CERN data repository, and we uploaded everything onto GitHub. So now it's free and open for everybody to go back, check what was done, recreate it themselves, and then the candidates will be hopefully available for many years in the future for everybody to go back and check. Okay, so just some quick results. Hopefully everyone's well aware of what the magnetic field looks like. So we've got declination maps here. The dotted line shows the agonic line where declination is 0. You can see blue is where it's pointing west of true north, and red is where it's pointing east of true north. And in the inclination, you can see the effect of the South Atlantic anomaly, and then in the total field at the bottom, you can see the strength of the magnetic field. You've got these effectively two large lobes in the northern hemisphere. You've got the large southern hemisphere lobe, and then you've got the South Atlantic anomaly sitting quite obviously there. And then the rate of change looks a bit different because you're looking at how things are moving. And then you still got this kind of strong westward drift over the the Atlantic hemisphere, and very little relative change over the Pacific hemisphere. Okay, the public outreach for this, I did a lot of press around the time, as did Will as well. You might have seen me, heard me on the radio in Britain. I was on the radio 3 or 4 times. Couldn't get enough of me. But what they're really interested in is like the magnetic North Pole moves, and you're like, yes, it does. And it's a little bit like people have a goldfish memory. Every 5 years, people go, what? The magnetic field moves? And you're like, yes, that's why we update the maps. You know? And then is there any kind of like problems with, I don't know, satellites or whatever, the usual kind of inquiries you get. GPS, was my GPS going to fail? No, it's not related really, but it's part of the system. So you can see that the North Pole continues to now move towards Siberia. The magnetic South Pole is drifting offshore. The red dots are the dip poles where the field dips at 90 degrees into the ground. The blue dots are effectively the equivalent, just dipole version of that. And the rate of change of this pole, North Pole in particular, moving has slowed down rapidly over the last few years. We got caught out several times by underestimating this in the past. So, but it is slowing down, and it slowly still continues to move towards Siberia, but not at the same rate as it did 20 years ago. Okay, how good are the candidates, and how often do we, why do we update this every 5 years? Well, the answer is because the rate of change at any given observatory is quite unpredictable, particularly given these geomagnetic jerks, for example. So here's the sort of a plot of Vesuvius Observatory in Brazil, which is near the South Atlantic anomaly, which is why I picked this one. And you can see that the candidate models are just shown as those various dotted lines right towards the end, from 25 to 2030. And there is a fair amount of spread, but you can see within the secular variation in the X, Y, and Z, there's also a fair amount of spread over time anyway. So which one of these models will be right in 5 years' time? Well, we'll find that out. And then whoever is the winner gets a round of applause at an IAGA meeting or something like that. So, but there's no prize really, but just you get the glory, get the honor. Another way to look at this is at the core mantle boundary, just looking at where the radial field is 0, and each of these models sort of shown for 2020, so you can see the models are quite closely overlapping. There's some kind of difference near the Caribbean, that's the main difference as far as I can tell. And then for the 2025 models, you start to see a little bit more variation. And in some of these models, the reversed null patch in the southern hemisphere is actually starting to combine together to become even larger, just where I've shown the arrows there. So these patches probably will merge by 2030 in the next few years. Okay, just other points of interest for the general public. The lowest point of the field is, for this particular model, it can change depending on what model you use, is over Argentina. It's roughly 22,070 nanotesla. That second point over South Africa, or just off west of South Africa, continues to deepen. And so the South Atlantic anomaly is still growing larger. The North Dipole and the South Dipole will actually briefly coincide in longitude right about this time, actually, roughly about March 2026. So they're both at minus or 136 east, which is probably hasn't happened before, or certainly not in the last few hundred years. And then these bursts of secular variation in the Pacific and East Indian Ocean are still ongoing, and actually they're typically the regions of the largest misfit in the model. Okay, so just to summarize, you've all contributed to producing this map, and the public thanks you. It's freely available for everybody to use, gets embedded in all kinds of systems that we probably don't even know about. One thing that we haven't really cracked in the last 20 years, despite having all this great satellite data, is that our prediction by the end of the 5 years really hasn't changed in the last 4 generations. So maybe that's something we can work on with all this new data. Maybe there are new techniques. Maybe it's not a data problem, it's a technique problem. So, for example, physically informed neural networks or machine learning techniques might come into the fore. There's a special issue that is almost complete. We're just waiting for the last 2 papers to be approved, and then we should hopefully get finally the official IGF 14 paper so that you can all cite it in your next papers, and make sure that everybody gets a great citation number on their record. And finally, yeah, looking forward for IGF 15. That won't be me, that'll be Clemens, I guess. So good luck, Clemens. But we'll have a plethora of data, hopefully. We've seen some of the new satellite missions coming through. And so it will be a case of what data to pick rather than not having any data at all. So thank you.
Hello, everyone. Happy to be here this morning. I will present you some of the results we've had with a previous project we had sponsored by ESA, which was called Swarm and MSS core. And there is a new an extension of this consortium with the 4D Plus project that gathers efforts by people from DTU, Leeds, Paris, and Grenoble. So you are now aware that there's an increasing constraints on the variation of the magnetic field originating from the core. I give here one map of, one time series of the secular variation, the rate of change of the field in Kourou, in French Guiana. So you see these rapid changes, interannual changes. This is at the surface of the Earth. And when using Swarm, MSS, and other satellite data, we can build field models down to the core mantle boundary. And when we look at the rapid variation, this is nanotesla period, that's the secular variation filtered in time. You can see as a function of time and longitude here, it is at the core equator, that you have these oscillating patterns, some westward propagation, eventually some eastward propagation as well on various length scales. This is all, of course, dependent on the finite resolution we have for these changes at the surface of the core. But there's a lot of information to chew in order to try to understand the physics below the core surface. So from this variation of the field, we have discovered the presence of waves. So these are hydromagnetic waves. It is motion of the fluid, but also perturbation of the magnetic field inside the core. These are called QG-MC. QG is for quasi-geostrophic. That means much influenced by the rotation of the Earth by the Coriolis force. And MC, the M is magnetic. That means the restoring force is not only the Coriolis force, but as well the magnetic field in the magnetic force in the core. We see the westward propagation of patterns here. This is at the core equator again over more than 20 years. This oscillating pattern at a period of 6 years were first discovered from satellite data, but an reanalysis of a longer series, including ground station, have shown that we have actually very similar patterns. If we look at 6 years, this is extracted essentially from satellite data, and this pattern here is on 12-year period, also includes longer satellite ground-based series. So there were no reason for the 6-year signal to be a single isolated wave in the core. There is a good reason to think that these waves populate the spectrum of the magnetic field also on longer time scales. We now have some evidence for decadal changes, and Julien was mentioning potentially pluridecadal periods for similar waves yesterday. So we can also use a numerical simulation to make some dissection of the physics. We are now in a position where, with assumptions about the turbulence in the core, in the simulation, in what we call large eddy simulation, we parameterize turbulence, it is possible to generate simulations that are at Earth-like condition. This is one example of such simulation with fluid motion in red and blue, magnetic field in brown and purple. And using this simulation, we can isolate several things that we can witness or not with the observation. One of them is, for instance, the appearance of a thermal or buoyancy plume near the ICB that will generate what we call QG alpha waves. So QG, that's Z invariant because of Coriolis, and alpha because magnetic force is the one that is important. And as they move outward, these waves, they morph into QG MC wave, magneto-Coriolis. That means the Coriolis force enters the problem while the wave gets closer to the core equator. And this becomes much elongated in the phi direction. And this is these waves that we have witnessed, the second one, the QG alpha wave. We have not yet found them directly from magnetic data. I must stress that the speed of this wave is much faster than the fluid velocity. The fluid velocity, the fluid perturbation here is 5, maybe at most 10 kilometers per year. The outward propagation and westward propagation, we speak here about 1,000 kilometers per year. So that's that's 100 times bigger. So what should we expect from the core as a signal with the future mission we will have at hand? So if we look at the combination of MSS, Swarm, NanoMaxSat, we hope to have a longer time series, of course, because we have the data accumulate, but also we hope to improve the time resolution because of the low inclination mission. And we can look in simulation what we could expect. So this spectrum here is taken from the latest simulation by Julien at Earth-like condition. This is the spectrum of the secular acceleration, so the second time derivative of the magnetic field. And this is for several harmonic degrees, all normalized so that they have the same power here for comparison. You see that all these spectra for all the degrees, they superimpose, which is somewhat surprising. That means the decay in the power spectrum here does not really depend on the length scale we're looking at. What we have witnessed in QG MC waves is somewhere here between a couple of years and some 10 to 20 years, okay? The spectrum is becoming smaller and smaller, so it will be more and more difficult to find the signal. But you see that happen some resonances at periods that are close to, close to 1 year. There is no relation with the Earth's orbit. But on periods close to 1 year, we have QG alpha waves there. We have not witnessed them yet, but if we are able to push the resolution towards the right here, there might be a possibility to detect these things and also to better dissociate using this kind of information about the spectrum for the magnetic field to better dissociate what's coming from the core from what's coming from outside the core, which could be induced signals that would be hiding somewhere here, the core signal. And of course, the mantle will filter the very short time scale here because of the screening. So these waves, why are they interesting? There are several things we are interested in with these waves. One of them is the coupling with the mantle and with the inner core. The fluid motion in the core, they can move in average east or west. And if there is a coupling with the mantle, this will generate changes in the length of day, changes in the speed rotation of the Earth because of angular momentum conservation. On subdecadal period, there are several spectral lines that have been isolated in the length of day that generate this kind of signals. So the observation is in red, and our prediction from a flow model inverted from magnetic data are in blue. So the overall fit is good given all the assumptions we do. The motions that are responsible for that are axially invariant, so these are zonal motion of that kind. And we have a bunch of waves, torsional waves and QGMC waves that could be that are candidates to explain this signal. And then the question is, what is the mechanism to couple the fluid to the mantle? So there are several candidates. One possibility is the electromagnetic coupling. A gravitational coupling involving the inner core is also possible. And the dominant torque might also depend on the frequency, depending on the properties of the deep Earth, like the viscosity of the inner core. So these waves are very interesting because they allow to probe properties of the deep Earth and to better understand how our planet is working as a whole. So some more detail about the mantle conductivity. This is a sketch taken from a paper by Stuart Russell. This is the core, this is the radius, and this is the mantle here. The conductivity of the core is usually much bigger than the conductivity of the mantle, okay? But very close to the core mantle boundary, there are some evidences that the conductivity should be relatively high because either the silicate are molten or because of changes of phases, and the proportion of iron is very badly constrained in this body. So you have ultra-low velocity zone here, imaged by seismologists, where the conductivity could be maybe 1/10 of that of the core. This is all debated. It is very difficult to sound the mantle conductivity when using induction from above, using the magnetosphere. You need long periods. I mean, people are working on that. Alexander Greiver is working on that. It is difficult because we need long time series and because of the ambiguity between the induced field and the core field. It is there are further ambiguities because the mantle will filter the high frequency signal, and we cannot exclude a strong conductivity here when using kinematic model like core flow inversion as we do. For this, we need a dynamical model that really couples the physics of the core to the electrical current in the mantle. So there has been actually only one study that did that, and it was based on the fact that the torsional waves, this is one family of waves we have isolated that are illustrated here on this time radius, cylindrical radius diagram. You see things that move outward towards from the inner core towards the core equator, and you see there is very little reflection at the equator of the core. The property of this wave is such that the reflection property is governed in particular by the mantle conductivity, electrical conductivity. So this is what is designed here on this plot. This is a normalized measure of the mantle conductivity, and this is the reflection, the percentage of energy of the wave that is reflected. And you see that for certain value of the conductance, you have no reflection. So this study is with an axisymmetric background field. So it has to be generalized to a non-axisymmetric field. But there is some physics to chew here in order to understand the processes at work in the deep Earth. And the waves will help us to do that. Another geophysical observation of interest is the fact that the inner core is not static in the reference frame of the mantle. There is differential rotation. This has been found by seismologists who, for instance, look at repeating earthquake that come from in polar direction that just sample the upper part of the inner core. And if you look at several earthquakes, sometimes you have the case of 3 events here where you superimpose events 1 and event 3. They superimpose very well, whereas event 2 and 3 and 1 and 2, they do not superimpose. And this can be explained by in two ways. Either you change the shape of the inner core or you change you rotate the inner core. The inner core is electromagnetically coupled to the fluid. So the dynamics in the core will change the rotation of the inner core. There is no doubt about that. But the inner core is also potentially gravitationally coupled to the mantle. So there is some physics to understand here and to know in which aspect the fluid motion can entrain the inner core is of interest with potentially consequences in our estimation of the inner core viscosity. This has to be further investigated. One thing that is interesting with the waves is that when you have a wave, you have information on the medium that it goes through. In our case, it's magnetocoriolis waves, so it will sense the dynamo field. The dynamo field, we cannot measure it. What we measure is the potential field down to the CMB. But once you enter the core, there are electrical current. You cannot use the potential field approximation, and you need physics, okay? And these waves, the more wave we can see, the better will be the constraint on the dynamo field inside the core from observation. So there is a lot of science to be done here. This is one example from linear simulations by Olivier Barrois and Julien Aubert, where you see the fluid motion here as a function of time and longitude, and the magnetic signal associated with that. So these are linear waves that are numerically solved. There is a lot of information to be gained, but there is also a lot of work to be done because we don't know the null space of this problem. So there might be many models of the field inside the core that would be able to fit this kind of observation. And there is also some work to be done to isolate the mechanism of the filter of the magnetic signal through the boundary layer inside the dynamo. With this project that is there for now 2 years, we will propose a benchmark of the several inversion methods for the reconstruction of the core dynamics from magnetic observation. So I have listed here a non-exhaustive list of possible tools that you can use stochastic models anchored to dynamo. You can use dynamo-based inferences. You can use machine learning methods. You can also learn using dynamo series with neural network. You could project onto eigenmodes. There are several ways of doing that. There is an eigensolver developed by Felix Gehrig in the 4D Plus team, which take benefit of both if we're able to calculate eigenmodes in somewhat realistic condition, the benefit here is that you couple the spatial structure of the mode with its temporal structure. So it would be maybe a way to improve the constraints on our recoveries. I give here one example of these eigenmodes. So this is the flow, so the east-west flow in red-blue, and this is the associated magnetic perturbation. So of course the observation won't tell us in all these details, and it might be even more complicated as the background field gets more complex. But we have eigensolver able to show this kind of pattern. So stay tuned. We will launch a benchmark in the coming months. So I conclude now. I think it's time for everyone to go to lunch. With a longer coverage from space, we hope we can have a tighter constraint indirectly of the geophysics of the deep Earth. We can use these waves in many aspects to sense the dynamo field, the electromagnetic properties of the deep mantle in link with seismic observations. And we will propose a benchmarking exercise on the core flow inversions. And I stop there. Thank you.
Do we have any questions for Nicolas? Alexander?
When you say sense and electrical conductivity of the lower mantle, do you still think it will be mostly the conductance sort of, or do you have an ambition to distinguish the radial? Only about conductance still, or radial profile?
So it depends, I think, on how you work. When working, for instance, on the mantle filter, I'm not sure that the conductance is the most relevant integral quantity of the mantle. So the dimension, the lag, for instance, introduced by Bacchus might be more relevant in that case. If looking at the physics of the core, we should start simple. So starting simple means a thin layer approximation to start with, in which case conductivity, conductance, I mean, you won't be able to separate. So I think it depends on the tool you use and of your target. But I would start simple because we are at the very beginning.
And Frederick?
Thanks, Nicola. I was wondering if you could elaborate on what benchmarking large-scale flow or fast dynamics.
We have several targets in mind. One is snapshot, okay? Snapshot means dominated by long periods. But, and this will be snapshot from dynamo simulations. And the other target is time changes in the flow. So this would be likely from path simulation from Julien. And there is an interest to look at the two separately because we know that the null space of the inverse problem for the transient motion and for the snapshot, I mean long period motion is not the same, coming from work by Anna here. So there will be both. So there will be a family of exercises, and a bit like in an IGRF spirit, people will be free to submit candidates to only a subselection of the exercise we propose. We will also, I mean, it has to be confirmed, but we will also propose a blind test and a test where we give the solution so that people can try to improve and find bugs in their inversion tools on the one side, and also testing in blind situations so that we are sure people don't cheat, basically.
One last question then. Could you repeat the question?
Yeah. The question is, can the QGMC wave excite changes in the inner core rotation? I think they are, okay, let's go back here. The QGMC waves, we essentially witnessed them in the external part, I mean, at relatively large cylindrical radius, okay? So if you look at eigenmodes, they will be everywhere, of course, but in dynamos like that, what we don't see QGMC wave very clearly close to the ICB. What we see here is QG-alpha waves and torsional waves, which are axisymmetric. So I would be tempted to think that the zonal part is will be the one that is most important to make changes in the inner core. But I might be wrong because you might have a QG eigenmodes which also have a zonal part in the tangent cylinder. That I don't know. It has to be investigated. So I would be tempted to say that might not be the most important, but I might be completely wrong.
Thank you. Thank Nicola one more time.
Please.
Okay, so our first speaker this afternoon is Anita. We can get everyone to take their seats, please. Also, just Kathy's reminded me that is a separate set of talks, public lectures next door in the Jolsock. And between 3:30 and 4 o'clock, there is tea and biscuits if you want to go there. And then there's a talk by Dr. John Coxon, if John's around. And he'll be talking about ionospheric current systems, which is somewhat related to swarm, I guess, and then magnetic fields, stuff that we're talking about here today, and sort of definitely related to stuff that's in this afternoon session. So without further ado, I'll introduce Anita, and you can give us your first talk. The clicker.
Okay, so I'm going to talk a little bit about the ionosphere-thermosphere research we have carried out at University of Oulu in Finland, together with my team members and other co-authors. How can I change the slide?
Okay.
Okay. And the outline of my talk is here. So first I want to give a little bit background to the ionosphere-thermosphere system and geomagnetic storms. And then I briefly introduce some of the most important instruments we have used in our studies. And then I will go to some of our recent studies carried out under this ESA's 4D ionosphere joint project. Then a little bit about this Mother's Day superstorm. And finally, one study about ionospheric cusp dynamics. And then I try to summarize some of the open questions we should study and some future prospects. So first, ionosphere-thermosphere. So in this plot, oops, okay, I perhaps should not use this. Oh, not wrong direction. Okay, on this plot, on this left-hand side, you can see a schematics of the ionosphere. And we typically talk about ionosphere between 70 and 1,000 kilometer altitudes. And that is a region where you also can find aurora borealis. That is also where you have the International Space Station, several ionospheric satellites. And then the neutral atmosphere at these altitudes, that is called the thermosphere. And these ions and neutrals, they have complex interactions. So we could say that ionosphere is the region where the space meets the atmosphere. A few words about geomagnetic storms and substorms. And this animation is actually describing what is happening to Earth's magnetic field and magnetosphere during a substorm. And the solar wind is coming in this animation from the left-hand side, and then it interacts with the geomagnetic field. And I will not go to the details, but you can see that many things are happening there. And the typical timescale for one substorm is about 3 hours. And the other concept is a geomagnetic storm. And typically during one storm, we can have several substorms. And storms can last for hours, from hours to days. And one very important property of the storm is that the ring current in the magnetosphere is greatly intensified during storms. You all obviously know quite well the Swarm satellites, but I still repeat some of the basics. So they are polar orbiting satellites between 400, 500 kilometer altitudes. And they carry quite many kind of instruments. And in our studies, we have utilized most of them. So there are these magnetometers,
there is the thermal ion emitter, which gives us the electric field. There are Langmuir probes, there are GPS receivers and accelerometers that can provide estimates of the nuclear density. And in general, these satellites, polar orbiting satellites, are nice because they provide us with very good latitudinal coverage of things. But then if you want to have information above a certain latitude, you get that only once per orbit, which is roughly 1.5 hours. Then when we go to ground-based instruments, so one very important instrumentation for us are incoherent scatter radars. And there on the left-hand side, you can see the ASCAT Svalbard radars. And here on the right-hand side is the ASCAT 3D radar, which is currently being built in northern Norway, also in Finland and Sweden. And additional ground-based instruments are, of course, magnetometers, aurora cameras, interferometers, and so on. And the benefit for ground-based instrumentation is that they provide a continuous time series over a given location. But of course, their field of view is very limited. Let's now go to some of the results. So Joule heating is one of the very basic important parameters. So it describes the electromagnetic energy that is coming from the magnetosphere to the ionosphere. And in our team, Heikki Vanhamäki has developed a nice method to estimate the ionospheric global Joule heating based on measurements by the network of SuperMag magnetometers, SuperDime radars, which provide the electric fields, and Iridium satellite magnetometer measurements, which are also globally covering the Earth. And then you can see these results of Joule heating changes. This is a statistical map, so-called superposed epoch analysis. And you can see on the rim are the magnetic local times, and then you can have latitudes. Noon is on the top, midnight is in the bottom. And now the time series is starting, so there is very little Joule heating before the storm onset, but then as the storm starts, the Joule heating is going to have higher values, and typically we have higher values within the outer oval, also to some extent in the polar cap. And here I have two panels. So this upper panel is the integrated Joule heating in the northern hemisphere, and the lower panel is the analysis of the nuclear density changes at about 450 kilometer altitudes based on Swarm and Grace measurements. And as the Joule heating is getting up, also the density enhancements start to be visible in the data, and the statistical median is over 100% increased compared to the quiet level baseline. Then I go to the superstorm. So this May 2024 event that was driven by the coronal mass ejection. You can see the solar surface. There was an active region, so very big group of sunspots, and around those several coronal mass ejections were launched, and they hit the Earth's magnetosphere, ionosphere, caused the storm effects. And I here just focus on some of the high latitude observations. So these color panels here, they show the ASCAT Svalbard measurements. So the bottom panel shows the electron density, and then the electron density change. And here are several days. So the storm onset is here. And after the storm onset, practically the ionosphere was wiped out. The electron densities became very small. And during the same time, we had clear enhancements in ion temperature. And those ion temperature enhancements are related to increased Joule heating, increased electromagnetic energy input to the ionosphere. And the physical mechanism of this wiping out of the electron density is in the fact that the recombination speed or recombination rate of ions is greatly enhanced. Then still during this superstorm here is the total electron content variation. So actually it is the actual total electron content shown. And this movie will soon start again. And in the beginning of the storm, there should be polar cap patches going over the polar cap. Now they come soon. Now they go over the polar cap. After that, there will be, they still go, but after that there is a lot of this blue color, and this is the depletion in total electron content that we also saw with the EISCAT Svalbard radar. Okay. What else happened? So again, some swarm observations. So this panel shows the swarm A neutral mass density measurements, and after the storm onset, we saw a very clear enhancement in mass densities lasting for about 1 day. The top panel shows the time satellite measurements, and basically it is telling us that the N2 molecules, their relative abundance to O is increased. So this is again related to the upwelling of the thermosphere. And maybe one more thing, so this paper has just come out, is that we show that the estimated Joule heating rate in the northern hemisphere was exceeding 1 terawatt during this event. And the last thing I wanted to tell about is a CASP study using swarm satellite and again EISCAT's radar observations. And first, why CASP is interesting is the figure on the left-hand side. So that is the region where the solar wind particles have a direct entry to the Earth's ionosphere. And those feed lines map to very high latitudes on the day side. And often the EISCAT Svalbard radar on the day side is within the CASP region, but not always, because this CASP location varies in latitude depending on the IMF conditions. And during this specific event, there was also the Svalbard swarm overpass over the CASP, and I will show some of the measurements by the swarm satellite. And here again, I have a plot with quite many panels. So let's start from the top panel. So this is first of all, this is latitude, and the parameter shown here is electron temperature. So we have a typical electron temperature enhancement within the CASP, and this is caused by very soft particle precipitation. Then this panel is showing the thermal ion imager measurement, and there are quite high ion velocity regions within the CASP region. And within those regions of enhanced velocities, we also have enhanced pointing flux downwards. Pointing flux is of course calculated by, it's basically this delta E cross delta P. And then we have up and downward feeder line currents, and from the magnetometer measurement, and the last panel is the broadband extra low frequency wave turbulence that is often observed, for example, within aurora oval. And all in all, this ionosphere thermosphere is a very complex region. Many kind of processes are taking place there. And there, of course, are very many open questions. I just put here a few ones. So the first one is, why does the sun and the solar wind magnetosphere coupling, or how does it drive this Earth's ionosphere-thermosphere system, how these parameters vary during storms, and what are the key drivers. How important are the small-scale structures, for example, in Joule heating, which are not always resolved by measurements. How large variations we can have in the nuclear mass density affecting LEO satellite orbits by atmospheric track. And then about the future, so I was very happy to hear that Swarm is still going to continue because it has so nice measurements. Then in the future, we will have SMILE and Aurora C, and as we have heard, NanoMaxSat, MMS-2, and EISCA 3D as the ground-based instrument. But all in all, this ionosphere-thermosphere region is difficult to observe. There are many complex processes, and we would definitely have more measurements than the magnetometer measurements. We would like to have magnetic, electric field, electrons and ions, nuclear densities, optical observation, everything. We need everything to understand what is going on. Then I would also say that combining ground-based observations and satellite data is essential. And also this ionosphere, we have, that is now the site of quite many satellites, so it's very important for us to understand what is going on there. And we have shown that in some of our papers that even quite small storms can cause significant changes in the ionosphere-thermosphere system. But what about if we would have more extreme events like this Carrington storm in 1958? That was something we have not seen after that, or even some millennium events like this 774 AD event, from which we have only some evidence from cosmogenic isotopes. So this is my end. Thank you.
Okay, thank you very much, Anita. Any questions on her presentation? Oh, sorry, Alexander, yeah.
You were showing some impressive high-resolution animation of text.
Yep.
During the meeting. I couldn't quite catch. Was it the ground station?
Yeah, so this is, they are global navigation satellites which send the signals to the ionosphere, and the receivers are on the ground. And from those measurements, we can derive the total electron content in the ionosphere. We don't have altitude profiles like from radars, but we have the total electron content.
Thank you very much. Was there a question over here? Was it Hannah? Yeah.
What we should be doing in the future.
Okay, so the question is, how do you combine ground and satellite data?
Good question, for which there is not a simple answer. It depends on, of course, what kind of ground-based things. But what we typically do, of course, when we make the comparisons, the first requirement is that if there is one single satellite, it must fly over our ground-based station. And that is to some extent perhaps challenging thing. So you should look at our papers, how we are. There is no one single answer how to do it. But when I look back what I have done, I almost always have done so that I try to combine both of them.
Okay, one is a quick, John? Yeah, yeah, okay. So there's a reference to a Rystat paper that people can look at.
And I would say also there is this Vanhamäki paper, which is soon coming out in JGR, where he also combines ground-based and satellite, these iridium satellite things into Joule heating. But there are many ways one can do it. There's not only one single way.
Okay, thank you very much. We'll thank our speaker.
So a very good afternoon to everyone and welcome along today. So what we're going to be talking about for the next 15 minutes or so is we're sticking with the ionosphere and we're looking at some results from a project called Swarm VIP Dynamic. VIP stands for Variability of Ionospheric Plasma, so it's fairly obvious what we're looking at there. And this was funded by ESA as part of the 4D Ionosphere Framework. So as you can see, it's a really big team. A very fast disappearing team as well, but it's a really big team. Huge thank you to everyone on the team and all the institutions who've contributed to this work. So what are we looking at within this project? Well, what we're trying to do is we're trying to create models of the variability of ionospheric plasma at multiple scale sizes. We're interested in the relative importance of the driving processes and creating a model that can come up with some predictions of that variability. So that's what we're interested in looking at. And of course, there's all sorts of methods we could do to create those kinds of models. And these days, we'd use all sorts of things with high computation, which require a fair bit of computational power, like neural networks and so on. But what I want to do is I want to take you back in time. Let's go back in time to 1984. Queen, Elton John and David Bowie were in the charts. The Olympics came to Los Angeles and Maycock and Hall published this report here called Accidents at Forearm Roundabouts. Now, what they wanted to do is they wanted to come up with a statistical model about accidents at forearm roundabouts in the UK. They didn't have the computational power that's available to do things like neural networks. So what did they do? Well, they used a technique called generalized linear modeling, a very simple but a very powerful technique. They were interested in making predictions of the number of accidents. They were interested in determining the relative importance of the processes that were linked to those accidents. So you can see how that method's really useful for what we want to do here. We want to make predictions and look at the relative importance of the underlying processes. Okay, so what is a generalized linear model, which we're going to use within this talk today? Well, a special case of a generalized linear model is a linear model of the form y equals mx plus c, shown in its colloquial form in the top right of the slides and in a slightly more formal manner in the center of this slide. Another special case of a generalized linear model is a multivariate linear model, where we now have multiple driving terms on the right-hand side. And a generalized linear model, well, the equation looks similar, but the difference is that the dependent variable doesn't have to follow a normal distribution. It can, but it doesn't have to. And if it doesn't follow a normal distribution, we often find that the equation on the right-hand side needs to take a different form. Okay, so what's our dependent variable? What are we trying to predict? Well, one of the things we're trying to predict is the electron density, but we're also interested in predicting some other things as well. We've got these very wordy definitions down here, but what it boils down to is we're interested in predicting the electron density and its variability on different scale sizes. So 5 dependent variables there, 5 things we want to predict, 5 models. We're also interested in then thinking about this in 4 different latitudinal regions. We suspect the drivers are different in these latitudinal regions, so we're creating different models in the polar, auroral, mid-latitude, and equatorial regions. So 5 dependent variables, 4 regions, that's 20 models we're trying to fit. And for each of those, we need to decide what distribution is appropriate for the dependent variable. So it can be basically anything we want, but we need to know what it is. So how do we work out what it is? Well, we're going to use things called quantile plots. So the idea here is, suppose the normal distribution was a good choice. Well, the normal distribution is set by the mean and the standard deviation. So we could take our data for the dependent variable, we could find the mean and the standard deviation of that real observed data, and we could use that mean and standard deviation to create synthetic data. We then create quantile plots, where we put the quantiles of the synthetic data on the x-axis and the quantiles of the observed data on the y-axis, and if the normal distribution is a good choice, all these points line up on the x equals y line. You can see here that the normal distribution is a poor choice. We tried lots and lots and lots of other distributions, and we tried not just those distributions, but we tried the transformations of them as well. And we manually inspected about 5,000 plots, which took a little while. You can see here, this is still not a great choice. Look at these points here diverging from the x equals y line. you can see there at those points that the quantiles of the input sample, so the observations, those values are always greater than those in the synthetic data. So that tells us if we use this distribution, the model we come up with is never going to effectively predict the higher values. It's never going to deal with the more extreme events. So after we went through all sorts of different things, we came up with a variety of good choices, and there's just a few of them there. So now we've got our distributions. Then we need to fit our model. And so the question we're asking is which combination of the heliogeophysical proxies that we could use, and hence which let me rephrase that. What we're asking is we're saying we're going to use a whole bunch of proxies for the underlying processes. Which combination of those proxies best explains the variability we see? So we're going to have a look at all those proxies. We're going to take the one which has the most statistically significant relationship to the dependent variable, to the thing we're going to try and predict. We're going to pop that in the model. We're then going to see which of the remaining proxies is best at explaining the remaining variation. We pop that into the model, and we keep going until no more proxies are available. And we come up with a whole bunch of equations. What are we trying as our heliogeophysical proxies? Well, lots of things. I'm not going to go through these in detail, but we've got various measures of the solar wind, the interplanetary magnetic field, geomagnetic activity, solar activity, thermospheric density, the current systems, and functions to represent the daily and seasonal variation. So we're using a training data set to fit those models. Then what we're doing is we're using an optimization data set to refine those models, where we refit those models and have a look at the parameter estimates we've got for them. And then we're using an evaluation data set to see how well these models work. We're trying to use models to predict the points in the evaluation data set, and then we can assess how well the models work using a variety of goodness of fit statistics. And the key point is all local times, seasons, geomagnetic and solar conditions are captured in each of these data sets. So what statistics are we using to evaluate these models? Well, we're using 4 of them. The first of them is a measure of accuracy, the root mean square error on a relative scale. So the ideal value of that is 0. We're looking at a measure of bias. We're looking at the mean error. Does the model consistently overpredict or underpredict the observations? So again, our ideal value there is also 0. We can look at the precision. That's the ratio of the standard deviations from the model to the standard deviations from the observations. Do we have the same amount of variability in the model as in the real world? If we do, our ideal value is 1. If we don't have that ideal value of 1, then it's telling us there's either too much noise in the model values, or it's telling us that there isn't enough spread in the model values. If there isn't enough spread in the model values, then the model is overfitted. So it tells us something very useful there about the model. And finally, we're using a measure of association. That's a Pearson linear correlation coefficient. Are we capturing the underlying trends? And our ideal value there is 1. So if we look at our models of electron density, how do they do? Well, when we look at the measure of accuracy, that's not too bad. When we look at the mean error, we have very little bias in our models. That's good news indeed. When we look at the precisions, these are approaching the theoretical best value of 1. That's really good news. If we've got the same amount of variability in the model as in the real world, we're capturing those processes quite nicely. And the correlations are a little bit less than 1, but they're not too bad either. Until we get to the equatorial region, where the polite way to say that is there is substantial scope for improvements. Now, let's look at the other dependent variables. What's going on here in this massive, massive, massive table? Best illustrated with the top right-hand cell, chosen because it looked pretty when I laid it out like this. And what you can see here, as we go to the smaller scale sizes, the goodness of its statistics get worse. So it works for electron density. We're happy with the method. But as we go down to these smaller scale sizes, this tells us that there could be a process missing from the models. And there's 2 key candidates: instability processes or wave activity from the lower atmosphere. Now, we can't test for instability processes here because we just don't have what we'd need within the data set to be able to do that. But wave activity from the lower atmosphere, now there is potential to be able to test for this. There's a team called Quidregis, based out of DLR in Germany, who've been coming up with all sorts of measures of wave activity. across Europe. And we could try those as explanatory variables in our models. And then we could see, is that the missing process? If it is, great. If it isn't, then it's probably this one up here, the instability processes. What we've also been doing is been comparing the Swarm VIP dynamic models to TIGCM. Now, TIGCM is a physics-based model of the ionosphere and thermosphere used by all sorts of researchers and around the world and used in various operational settings as well. So what we needed to do is we then took a subset of the data from the evaluation data set and re-evaluated the goodness of its statistics for Swarm VIP dynamic models just to that subset. We then did the same thing for TIGCM, and then we did the comparison. Now, where there's green values here, the Swarm VIP dynamic models outperformed TIGCM. The red values are where TIGCM outperforms Swarm VIP dynamic. And so you can see here that the Swarm VIP dynamic models outperform TIGCM in 3 of the latitudinal regions. You can see a reduced bias and improved precision. But of course, the Swarm VIP dynamic models only work at 1 altitude. But this does lead to a very intriguing idea. Could we take the Swarm VIP dynamic models and use them to correct biases in models like TIGCM? Could we, for example, take a data assimilation scheme like ANEAS that was developed at the University of Birmingham, and could we feed in the model predictions from the Swarm VIP dynamic models as if they were an observation and use that as a way to correct the biases that are present in TIGCM? So there is an interesting possibility for the future. Now, the other thing I wanted to briefly mention is we said that in 1984, researchers weren't routinely able to use neural networks. Of course, people can now. What happens if we use a neural network? Well, what happens is we get goodness of its statistics that look like this, that go on and on and on forever. The Swarm VIP dynamic models are on the left-hand side. Then redoing those with neural networks is in the middle, and the differences are on the right. The green is where the GLM does better with the goodness of its statistics. The red is where the neural network does better. You can see in lots of cases the neural network does better. So why don't we use them? Why are you always sticking with generalized linear models? Well, there is a limitation. Let's go back to the quantile plots. And this is what we get for the neural networks. These points do not line up on the x equals y line. And they spectacularly don't line up when we get to some of the more extreme events. And so what this is telling us is it's telling us the neural network is making a bad assumption about the distribution of the data. And because it's making that bad assumption, the neural network might do a good job on average, but it doesn't capture the more extreme events. And so there is, again, something which is potentially a useful thing to consider when thinking about neural networks more generally, to do some tests to find out, are the neural networks making good assumptions about the underlying distribution of a given data set? Fantastic. So there's the summary of Swarm VIP dynamic. In the final 2 minutes, I want to move on to something else. And this is about a roadmap we're developing at the Met Office within the Space Weather Research Team for developments within the models that we run for the ionosphere and thermosphere. Now, there's a bunch of different models that we run to cover the ionosphere and thermosphere, and we're thinking about how to develop those across the next 5 years or so. So I have the most simple Venn diagram of all time here. We have science, we have applications, we have a roadmap in the middle. The idea is, what we're interested in the Met Office is we're interested in how we can get better, reliable forecasts which are actionable and useful to our users and customers. So we're asking these questions from a scientific point of view: what improvements are possible for the models? And from an applications point of view, what improvements are desirable? Because it might be there's something that is a really good scientific improvement in the model, but if it doesn't then create that benefit for our users and customers, well, it's a very valuable thing to be doing, but it's not one for us. So we've got this request for input. And so I'm very keen to ask for people's opinions on what people think are the scientific grand challenges on the horizon for our community working with the ionosphere and thermosphere. How could Swarm, MSS, all the various friends that go alongside those missions contribute to addressing those grand challenges, or contribute to validation and verification activities for existing models. I'd be very, very welcome to take any comments and questions in just a moment. I'd also be very welcome to have any informal chats as we go through the afternoon, especially over coffee. And of course, I'd be very, very happy to have any comments by email in the next few weeks as well. So I think that's where we're going to finish here today. Thank you very much for your attention, and I'll be delighted to take any comments or questions.
Thank you very much. Have we got any questions from the audience? No? Okay, cool. Well, Kathy's going to ask one thing, so Kathy first and Ravi.
Going back to your neural network, so I think you're basically saying that the models don't do well with the too often too quiet problem. So have you looked at other types of ML that are supposed to better address that problem?
Okay. So the question is, have you looked at other types of machine learning models that do better at rare events?
We haven't, but that would be a very, very, very interesting avenue to, that'd be a very interesting avenue to follow. And yeah, that would be a good logical next step in this work, absolutely.
Okay, and then Ravi.
Thanks for that, that was really interesting. I was wondering whether you'd taken, I saw you took all the different set of outcomes about when you had your correlation coefficient, whether you looked at when the model broke down. Did you mention this, or is this when you have higher events?
Yeah, so the question is, at what point did the models break down, and if you looked at the parameters and where that is?
Yeah, sure thing. So what we tried is we put, we made sure that there were a number of major so we were using roughly 10 years data, and within that there are quite a number of major geomagnetic storms. So we made sure that we got those in both the evaluation data sets, in the training data sets, and in the optimization data sets. And we specifically kept back some for the evaluation data sets, which would include some of these really extreme events. But not just that it would include extreme events, but it would also include extreme events where we had a whole bunch of other ground-based and space-based instruments available, so that we could evaluate just how well these models do. So I'm going to defer a comment on how well that actually works at the moment, because that's all still work in progress within the team. But that's going to become part of a paper that we hope to publish later in the year. So yes, so watch your space.
Okay, any further questions? No? Okay, well, let's thank Alan once again for a great talk.
Thanks for the invitation. And today I would want to share the contribution of my colleague satellite to the ocean induction studies. And this is our co-authors, and also Keke. And I come from the Central South University of China. And first, I will give a very short background, and I will show details how we selected the data set. And we use two methods to extract an ocean induction signal. And I will show the result and make a very simple conclusions. So here I want to share the real properties of MS-1 compared to other satellites. It has high precision, and also it has a unique low inclination orbit. And more important, it occurs more local times. And here I jump directly to how we select the data set. So in this study, we used 2 years of MS-1 data set, and also used 12 years MS Swarm A. And we use the single point measurements. We did not consider the gradients. We did not consider the north-south gradient and the west-east gradients. And the step one is we want to make sure to ignore the influence of the atmosphere. So we strictly using the index, the SZA, the standardization angle. So we make sure the angle is larger than 100 degrees. It means when any use satellite data set at this site. And step two, we want to make sure the environment of magnetic field is quiet. So we use several indexes such as HP13. So it has 10 categories. We make sure that we use the data set, the index is satisfied 0 in category 1 category and 2 category. So in this two category means so it's a very strictly required magnetic sphere, and we also measure the change of ring current rate. We make sure the rate is less than 2.0 lambda Tesla per hour. So the purpose is also going to make sure the background is stable. We also consider the solar wind. So we use larger measurements, the emerging electric field. So the amplitude is less than 0.8 minimum volt per meter. And so it means, and the exchange of the energy between the magnetic sphere environment and the solar wind is to be minimal. And we also using the BZ component of the carried by the solar wind. So we make sure it is positive. So it's directing from the south to the north. And as you can see here, this is the direction of the magnetic field. Because this magnetic field is parallel to each other, so the so-called magnetic reflection didn't happen. And it means the transition of the heat, transition the area between the solar wind and also magnetic field is kept to minimal. We also measure the index of the Y component. So we use the absolute value. We guarantee the absolute value of By is less than 3, and it makes sure the current along the polars are to be kept minimal. So all we do is try to make sure the solar wind effect is minimized, and also make sure the magnetic environment of magnetic sphere is stable and quiet. Because the ocean inductive field amplitude is very weak, and so we jump to step 3 we try to remove the effect from the core and crust, and also the external source using the chaos model. And the final model we want to, because we have different kind of data sets, such as vector and also the scalar. And for the polar range, we only using a scalar because we try to minimize the effects of the polar currents. And for the lower and middle latitude ranges, we will use the vector data set. Okay, so this is this is residual magnetic field. So we test four data sets. One is the panel A shows the result, the spatial distribution of the 2 years MSS-1 data set. The panel B shows the 2 years of Swarm A, and the panel C shows the 2 years plus 12 years Swarm A. And here the panel D is a distribution and property density. It means all the data sets and the standard derivation is quite close to 0. So from a statistical point of view, the data quality is quite good. And so we have the data set, but we needed the math model to fit in the data set. So we introduced we tested 2 methods. But the first one is based on the standard time and harmonic expansion series. It means the potential of the magnetic field of the ocean induction field can be expressed like this. And I want to draw your attention to the basic functions, which is highlighted by the red color. It's cosine omega t. Here, omega is the frequency of the tidal singulus. And so the limitation of this one is based on pure mass. Is based on the spherical expansion, and it ignores the physics information of the orbit of the moon. So maybe it's difficult to extract the race weak signals. And method 2 means we use the information of the orbit. So this expression is based on the gravity expansion of the gravity potential. So I want to draw your attention to the basic functions compared to the previous one. So we changed the cosine omega t to the cosine 2 times the delta L. And the 2 means we deal with the semi-delamer title such as M2 and also N2. And delta L is the true lunar azimuth angle. So it's a time-dependent angle. The advantage, as you can mention, as you can consider and as you can think, so we consider the real orbit of the moon respect to the Earth. So maybe it's quite good. So now for the method 2, how we extracted the specific tidal singulars. So first, we input the residual data set, and we use our EP model try to obtain the coefficient. And then we, using coefficient, try to generate the time series, and then we apply the TH model to extract the specific tidal singulars. Okay, so before I show the models, I want to show how the data fitting conditions. So also these figures show the data fitting result for the 4 data sets. And the left corner is for the 12 years Swarm A vector data set. And this one at the red corner, top right is the 12 years Swarm A any using scanner. And here is the 2 years MS-1 data set with scanner values. I also, so in each panels, I also calculate the standard derivation for the TH model and for EP model. As you can see, the EP model decrease the standard derivations. It has better fittings, and also if for the case of less number of data set, the EP method have very good performance compared to the TH method. So the value of standard derivation is improved by at least 20%. Oh, okay, I show the result. And so for the left side is the real part of the ratio component of the magnetic field for the M2 tidal singular. So as you can see here, for the 2 years MS-1 tidal singulars is quite close to the one with 12 years Swarm A data set. Also, I show the result from Graver as a reference result. So I can make a conclusion. So even with 2 years MS-1 data set, it can extract M2 tidal singular quite well, and to some extent, it has better performance compared to the data from the Swarm A. So similar conclusion can be obtained from immediate part. And this is a linear comparison of the spectric on the Earth's surface for the TH method. So as you can see here, so for the same period, 2 years data set, the power spectrum on MS-1 is stable in the higher order compared to the Swarm A. And if we combine these 2 data sets, the 2 years MS-1 and 12 years Swarm A is close to the model offered by Graver. And so here I compared the performance of these 2 methods. So the testing data set is the 2 years MS-1 and 12 years Swarm A. And the top column is for the result of the TH method. The second column is the result is the EP method. So as you can see, they agree to each other very well. And so this is a comparison of the spectral power spectric. So they also show very good agreement to each other. So here is my point. I also select the data set which is marked by the rectangle. So in the rectangle, I use 2 methods to generate the time series, and then I performance the analysis, try to extract the amplitude of different components of the tidal singulars. So as you can see here, both methods can recover M2 amplitude quite well, but for the N2, because it's very weak, its amplitude is very weak. The TH method cannot recover its amplitude, but the EP method can recover its amplitude quite well. So this comparison indicates the potential of the benefits of if we using the orbit information of the moon to extract the tidal signals. So this is a final comparison. So finally, we applied the EP method to extract the N2 magnetic field. So the data set is 2 years swarm and 12 years. Is 2 years MS1 and 12 years swarm A. We do not use the gradient information, but the signal column is from the Graver. He used this swarm ABC and the 10-year champ, and also both the measurements and the gradient data set. So as you can see here, so this new method use 10 times the next data set, but you can produce result quite good to each other, even for the very weak N2 singulars. So this is the conclusion. Maybe okay, this is comparison. Last comparison between these two spectra. So as you can see here, and our result EP method has very better result at the higher orders, and the difference is caused by in our study we only using the single measurement, single point. We do not use the north-south gradient or east and west gradients. Okay, this is conclusion. So first, I want to make sure to the MS1 is ready for the tidal singular studies, and also comparative combination with different satellites is better. And I also, the main point is, so even for a very weak ocean studies, the combination of mass and physics is better than the method and using the mass. Okay, so in the ongoing work, because we have different platform, I have a satellite, we have the ground sat. We also sometimes we have the measurements from the ocean bottom. So maybe we consider a combination all of this platform together to build a comprehensive ocean induction singular. So thank you.
Very nice work. Have we got any questions? Okay, yes, go take.
Okay.
How to add ocean bottom data.
I understand, yes. So in the EM Induction Society, we have the MT sounding on the bottom of the ocean. So sometimes we can put the instruments for more than 1 month. So the period is much larger than the period of the M2. I think it is possible. Yeah.
Perhaps a silly question, but since I mean, I guess you're going to use signal of the tidal signal in the ocean bottom.
Yes, you're right. Yeah. Yes, I think you're right. So this is just the initial result. So it definitely has some challenges. So we want to put these two different platforms together. Why? And because the tidal singular is unique, it's everywhere. So it's 3D distribution. So I think this is initial thought. Yeah. So I cannot answer you here because it is a challenge. I need to analyze more. Yeah.
So I've got a quick question. Can you look at, or I suppose the question more is, how long a time series would you need to look at the longer periods like the O1 and the O2, which are the longer tidal periods?
Here, so I mean, is less than both their periods is less than 1 day. So at least, so based on our experience, we test the 2 months of the satellite is not enough, and we also test the 5 months is also not enough.
Okay,
yeah,
that's just to see.
Yeah, we need a very long series because it's a very weak singulars compared to the Earth's main magnetic field. It's very weak singulars. So,
yeah. Okay, very good. Okay, any more questions? No. Okay. Well, thank you very much for your talk, and thank you, speaker, once again.
Okay. Okay. Good afternoon. My name is Hongbo Yao from Macau, and today I would like to introduce our recent or initial results about physics-based modeling of Earth's magnetic field. And this is the outline, and my talk will include many three parts: the background, and then I will introduce the field modeling method and the induction equation constraint. And then I will introduce our initial results using MS-1 and swarm data. So I would like to start from geomagnetic field models. And the geomagnetic field model, it describes the spatial and temporal variations of various magnetic sources, both inside and outside the Earth, including the core, the mantle-induced field, and the crust field, ocean-induced field, ionosphere, and magnetosphere. And currently, there are many geomagnetic field models, and including KELS, SAM, and BGM. And all these models have contributed to geomagnetic field modeling. And for our MS-1 team, we would like to develop physics-constrained geomagnetic field modeling framework and models which incorporate more physical constraints. For example, in 2024, we incorporate the electromagnetic induction equations in the Earth mantle, so we can better account for the Earth mantle-induced magnetic field. And in 2025, we also incorporate the electromagnetic induction equations in oceans, so we can incorporate the magnetic field induced by ocean circulation. And here in this study, we will focus on core field, and we will incorporate the magnetic induction equation into geomagnetic field modeling. So, and the frozen flux assumption and the magnetic induction equation is the form. And here the dBdt is the circular variation, and the U denotes the core flow, and B denotes the Earth's core magnetic field. And this equation shows that the interaction of core flow and the magnetic field can generate the circular variation. So from this equation, we can involve for the core surface flow, if we know the circular variation and the magnetic field data. And in the meantime, it also implies one thing, that the core field models should satisfy the magnetic induction equations. And but in most field modeling frameworks, this physical constraint is not explicitly enforced. So what we would like to do is to extend our previous field modeling framework to incorporate this induction equation constraint. And we also would like to investigate its influence on the core field model. So in our framework, this induction equation is enforced as an additional constraint in the model involving objective function. And this objective function includes the first term, the date phase between model prediction and the observations. And also, there are two transitional terms which minimize the third and second time derivative of the core field at the comment boundary. And here, in addition to these recognizations, we also apply another recognition which forces the field model to satisfy the magnetic induction equation. And this recognition is the following form. It includes the integration of the magnetic induction equations, also at the comment boundary. And here we can see the core flow and the magnetic field, both are unknown. So this problem is linear. And to solve this linear problem, we apply a iterative approach. And this approach alternatively estimates both the flow model and the field model. And here, this picture shows the workflow of our method. And first we have the data, MS-1 and so on. And then we perform traditional field modeling to estimate the field parameters without the induction equation constraints. Then we use this model to estimate a core flow model. And then we use the core flow model to estimate the field. And then until this process convergence, we have the field and the flow parameters. And should be noted that this our framework is different from the field flow co-estimation technique. And we use inertial modes to represent the flows in this study instead of the spherical harmonics. And this has two advantages. First, the inertial modes naturally reflect the dynamics of Earth's fluid core. So it can help to reduce the non-uniqueness of core flow inversion. And second, this parameterization can reconstruct not only the core surface flow, but also 3D core flow. And here, this is a sub-problem 1, the flow estimation. And here, with a combination of the inertial modes to represent the Earth's core flow, like the form. And these modes are defined in cylindrical coordinates, and it includes 3 parts. The first part is the equatorially symmetric inertial modes, and the anti-symmetric inertial mode, and also the geostrophic inertial mode. And the parameters mk and n count the spatial complexity of the flow in different directions, and the c coefficients are the unknown flow mode coefficients. And here, the u are the inertial modes, and they are served as pre-computed basis functions. And these basis functions propose the physical structural constraints on the flow. And this picture shows the distribution of about 4,000 inertial modes grid at the comment boundary, and it is computed in physical space. And so using this pre-computed basis function, it can avoid the need for additional regularization during flow inversion. So if we, here is the induction equation. So if we know the magnetic field and the circular variation, and we can write this equation in a linear form. And then the flow model parameters can be estimated in least regular least squares inversion. And in addition, and the MS-1 team also developed a more advanced framework using PIN. But here, I will use this simple framework. And here, for the sub-problem 2, the field estimation and the induction equation constraints, and we parameterize the time-dependent core field using spherical harmonics up to degree 15. But we also co-estimate the cluster and the magnetospheric fields. But we will not show the results for these 2 fields. And so the inversion objective functions with the estimated flow is known. It is written here. And then the model parameters are estimated using iteratively related least square method. Okay, so I will show the initial results using MS-1 and Swarm data. And here, we use over 10 years Swarm constellation data, alpha, bro, and Char-C, and both vector and scalar data we used. And for the MS-1 data, we use over 2 years of vector data. And here, in the following, we will compare 2 models. And the first one, model 0, was modeled without induction equation constraints. So its input is field model. And for model 1, it includes the induction equation constraints. And here, we use, for simplicity, we only use a steady core flow for model 1. Okay, and this picture shows the estimated core surface flows using different truncations of M and K. And here, the first panel shows the core surface flow of a PIN solution, and the right 2 panels shows the structure of the flow model estimated from this framework. And we can see very similar structure. And there we can also see the dominant feature of the flow is a large scale westward flow in the low latitude Atlantic hemisphere. And here from the right two panels, we increase the truncation parameter, but we do not see a significant difference. Okay, and here also shows the coastal flow, but use different truncations of N. And this parameter counts the equatorial symmetry of the flow. And here, the first one, when N equals to 1, and the flow is almost equatorially symmetric, and you can see the symmetric structure. And when it becomes large, and we will see slightly complex structure. So using inertial modes, it can provide a natural structure constraint on the flow. And here, we show the magnetic field model. And here, this picture shows a trade-off curve between the data misfit and the model roughness. And here, shows the need of the L cover. So we choose this damping parameter for model 1. And here, we first show the spectrum of the Wellen field in the left and the second variation in the right at approach 2025 for these two models. And model 1 without constraint and model 1 with constraint. And for comparison, also plotted the spectrum of chaos model. And here we can, in the left panel, we can see the three models show similar spectrum, but in the right panel, we show that after imposing the induction equation constraint, we can see a very clear difference in the SV spectrum for model 1. And this is because this field model is forced to satisfy the induction equation. So I think this is a result of a trade-off between date fate and physical constraints. And here, I show the global map of the circular variation at Earth surface in the left, and also the difference between model 0 and model 2 in the right panel. And here our model was resolve the typical structure of the circular variation at the Earth surface. It is strong SV single in the north, eastern South America, and also the negative and positive SV field in the west and the east of South Africa. And in the right panel, we see that after enforcing the induction equation, and we see distinct difference. And this is caused by the enforcement of the induction equation constraints. Okay, and here, I show the same maps, but at the commental boundary. And at the commental boundary, there are more small-scale structures in the SV map. And here, but the second variation difference becomes more remarkable at commental boundary, and it can reach up to 10 meter per year. Okay, and here your summary. And this is only our initial results. So and this work, we extended our framework to incorporate the induction equation constraints. And using this framework and MS-1 and Swarm data, I obtained self-consistent models of the core magnetic field and the flow. And the flow model satisfies the induction equation, and the core flow model is constrained by the inertial modes. And what we would like to do is to explore a better truncation, choice of the truncations of the inertial modes, which counters the spatial complexity. And we will also consider a time-dependent core flow. And okay, thank you.
Thank you very much for the presentation. Have we got any questions from the audience? So Chris has hand up first. I'll just repeat the question for the online people.
Thanks for the very nice talk. I have a question about flows at high latitudes. Is these inertial wave modes
they're designed for full sphere geometry, the full sphere models, right? So they don't include presence of inner core. So I wonder, is there challenges in getting the flow correct with this choice of inertial wave basis at high latitudes?
So, as if you want to get a more complex structure at high latitudes, I think we should adjust the truncation of n, but I didn't do much more tests about this, so I will do more tests in the future for this job.
Probably in order to capture the city inside the time to because the low frequency does not mostly stay outside.
Even principle can get them inside.
Well, because you still have the three structure will be the four. You have to capture more details inside the time.
I think Kathy was next.
Yeah, you indicated one of the advantages of your choice of modes for the flow was that you could investigate the flow in the interior. Have you looked at how it does vary with depth as you flow into the core?
Sorry, can you repeat?
So I think the question is, how does the flow vary with depth as you go into the core?
I mean flow vary with depth. Yeah.
Oh,
yeah, okay. Okay, I only show the core surface flow. Yeah. Okay.
Okay, so that question will be next. And there's one more from Gautier. Back up. You know you're not done yet. One more question.
I was just curious, how do you deal with the truncation? How do you know where you stop? How do you deal, perhaps, low degree or high degree or small scale flow with small scale, deep, large scale, something like that? So how do you deal in practice with the truncation levels of both low flow and
actually, in this paper, I didn't consider this. Yeah. But I think more tests are needed. Okay, thank you.
Okay, we'll thank our speaker then. Thank you very much.
Good afternoon, everybody. I'm Yu Fenling from Tech in Shenzhen, China. So first, thanks all the organizers, and it's a great pleasure to be here. So today I'm going to present some of the work we have been working on the geometric data assimilation using the ensemble gamma filter. So this work was mainly done by my PhD students Zhipen Zheng at Tech, and of course under the guidance of the Professor K.K. Zhang. So we know the Earth's magnetic field is generated in the Earth's outer core through the dynamo action, and which has probably operated for more than 3.5 billion years. So the dynamo process is really a complex system which involves multi-physics, low linear dynamics, and also over the wide range of the time scale and the length scale. So it's extremely challenging to understand what exactly happening in the Earth's core. Of course, as we heard from the Julie Abbe's talk yesterday, that over the past 3 decades, numeric simulation has significantly advanced our understanding of the geodynamo process. So actually, this plot on the left is one of the visualization from the simulation by Lassalel Shafat. Meanwhile, so we already have continuous satellite observation of the more than 2 decades. So that's why we are here. And of course, we would like to use this valuable observation to constrain, to help us understand what's happening in the Earth's outer core. So how could we do this? Actually, we already heard a lot from this 2 days conference. So the most classic and conventional way is start from the magnetic induction equation at the surface of the core. And if you use the frozen flux approximation, you would get a core surface flow. Of course, so this is one of the example we obtained use the PIN, use only the induction equation, use the Swarm and MS-1 data. So this inversion is highly unique. You need to make some assumption about the flow structure, mostly about the positrophic or column structure. And of course, if you use a different method and a different assumption, probably you get the different flow structure in detail, but the overall large-scale circulation remains similar from different models. And also, if we consider, as Hunbo just introduced, if we consider the rotationally dominated dynamics in the Earth's core, we may use the inertial modes as a simplified dynamics for the Earth's outer core. So we do the inertial modes expansion because inertial modes itself are three-dimensional. So the inverse problem becomes to get the coefficient of the inertial modes, use the circular variation of the magnetic field. And of course, this was realized to use the PINs again. And so that's well the structure of the three-dimensional flow structure we obtained use the Swarm and MS-1 data. So you can see that the large-scale circulation, so in particular the eccentric giant, which has been mentioned many times over this conference, and also you see the east-west hemispherical asymmetry of the flow structure. And you do see this, so on this side, you see this helixy column convective structure flow. And actually, you already heard from the Jin Feng's talk yesterday. He has extended this framework to consider the MHD dynamics. So today I'm going to talk about the more conventional approach, but to consider the fully dynamics. Of course, the technique is well known is the data assimilation, which has been introduced in the geomagnetism over the last 2 decades also. So the idea is to combine the geomagnetic observation with the numerical geodynamo models to estimate the states of the core and also to make the prediction of the evolution of the Earth's magnetic field. Broadly speaking, there are 2 branches of these data assimilation techniques. While the variational data assimilation, basically you estimate the optimized trajectory of the dynamics, which match the observation and also satisfy the dynamo equations. Of course, to get this optimization, you need a adjoint model or dynamo, which is technically and computationally very challenging. Another approach is the so-called sequential assimilation approach. So basically, you update the states step by step where there is observation available. So usually this is achieved by the Kalman filter using the statistic property of the dynamic system. And this statistics is usually using the ensemble of the dynamo simulation. So the well-known method is the ensemble Kalman filter, or in short, ENKF, which has been actually performed over the last decades in the geodynamo data assimilation. So basically, you start from a prior ensemble, which is a free run or from a previous forecast. And where there is observation available, you do the analysis, and the analysis relies on the Kalman filter. So which basically use the observation and also use the covariance matrix or the dynamo simulation from SMA. So that's quite a standard way to do the data assimilation, use the ENKF. In this talk, I will present, so we do one more exercise. So the classic ENKF only use only the observation from the past. But if we do one more exercise, so basically after the analysis at TI and you make prediction at TI plus 1, and then you do one more step. You use the observation in the at time TI plus 1 to do another reanalysis. Of course, this reanalysis is still use the Kalman field, but you use the covariance matrix between the dynamo simulation at TI TI and TI plus 1. And of course, you also use the observation at the TI plus 1. So actually, you can repeat this exercise for the time at TI plus 2 and even further. So under certain conditions, so this approach basically can be equivalent to the variational approach. Of course, we can't do all the future timescales. So we do basically, usually we do a two-step smoother. Actually, so this ENKS approach has been used to produce, this is the work from the LASA team. They have used this ENKS approach to produce the IGF-14 circular variation model, but they use only the frozen flux approximation for the dynamic model. So here we present some preliminary results to do the ENKS using the fully self-consistent dynamo simulations. So we start from some dynamo simulation at moderate parameter regime. So that's quite standard dynamo model in a spherical shell with fixed temperature, low slip, insulating boundary condition, and the simulation was performed using the X shell code. So that's the input and output parameters. And on the right, the plot also shows the force balance of this dynamic model. Of course, we produced the two models to compare the model errors. So the only difference of the two models is actually the viscosity. Of course, this model error is quite small actually compared to the model if we were to do the real observation. But anyway, so the summarize of this model we used is moderate parameter regime. That's which we have to do because we need to run ensemble, and I show you the SM size is a few hundred, so we can't do simulation at very extreme parameter regime. But even at the moderate parameters, so the force balance is kind of similar to what the Julia has shown yesterday. So it's a QG MSC force balance, and also this dynamo simulation also produce Earth-like magnetic field at the command boundaries, and also if you look at the flow and the magnetic field in the interior, so which have sufficient complexity of the system. So the exercise, so for the data assimilation, so we need to set up some parameters. So of course the ensemble size 256, and we do assimilation every 10 years, and we do the simulation over the time scale of the 130 years. And so of course for the simulation, because in order to use the COV-OBS model, so we rescaled all the simulation to the dimensional unit. We need to introduce the time scale and the strength of the magnetic field to match the COV-OBS. And one of the important things to achieve this is we need to do some trick on this, the so-called localization and the inflation. The reason we need this is because the ensemble size, even though it's 256, which is much, much smaller than the premise of the dynamo system. And also because the observation at the command boundary only deploy the magnetic field at the command boundary, which is only a tiny fraction of the whole dynamic system. So we need to do some trick. So one is the localization, so which is basically to avoid the spurious correlation between the long ranges. And also we need to do the inflation to avoid the overconfidence of the model. So if the model is overconfident, so basically we need to artificially increase the spread of the ensemble. Otherwise, the model would all the ensemble would converge to the same trajectory as the convergence matrix lose mean. So that does not make any sense anymore. So actually, this is the most tricky part because all the framework is quite standard. This is the most tricky part because there is no well-established guidance on how to set these parameters for the dynamo problem. So the only thing we can do is to do experiments, to do tests. And it's difficult because, as you can see, that the experiments is very expensive. So we did 3 experiments, and one is you compare the ENKS and ENKF alone, use the same model to produce the synthetic data, and the second test is to compared to test the model error, the effect of the model error for the ENCAX. So we produce observation, use the dynamo simulation from the lower viscosity, and we use the dynamic model for the large viscosity to do the assimilation. And eventually, we use we forced to did a test to use the real observation from the COV OBS. So that's some results. So the first is about the comparison of the ENCAF and the ENCAS. So that's the flow reconstructed after the 130 years assimilation. So on the left is the reference states, and in the middle is ENCAS and ENCAF. So you can see that the ENCAS slightly get more details about the flow structure and probably slightly closer to the reference. And on the right, that's the misfit of this ENCAF and ENCAS. So of course, the red color means a small misfit. So for some modes, actually the ENCAS indeed outperforms the ENCAF alone. And that's the cold surface flow. It's the same, so it's basically the same thing, but here we plot the flow at the cold surface and truncated and spherical degree 20. So again, it seems that ENCAS is slightly better. And also to quantify this, we use the correlation coefficient to quantitatively to measure the performance. You can see that in the out region, so the ENCAF is slightly better than the ENCAF method alone. And the second test is about the model error. So as I said, we use the data produced from the low viscosity dynamo simulation, and we do the simulation. We use the large viscosity dynamo simulation to do the assimilation. So there is, of course, as I should mention that in these two cases, the model error is really small. You can see from previous slides that the two models are essentially quite similar. But still, and you just add some imperfect models, so you get slightly reduce the performance of this method. So eventually, we, of course, we know there is a huge model error from the dynamo model we used here, but still, we did a practice, we did an exercise to use the COV OBS observation to get the cold surface flow. So that's the cold surface flow reconstructed from this approach. And so you can see the data assimilation gives you more small-scale structure. We do see the westmost flow in the equatorial region, but there is no obvious eccentric jar, as you often see from the cold flow inversion. Of course, you can see the once we do this, we can do the prediction of this model. So that's the predict. And also, we have the prediction and the analysis. You can see that ENCAS get a more smoother trajectory of the system. So this is the final slide, show the prediction. So overall, it seems that for most of the coefficients, it seems that ENCAS is slightly better than ENCAS. And also, although so the black line is the reference and it's the real observation. So compared to the linear prediction of the time scale 20 years, so we can see that the data assimilation indeed not exactly get the circular variation, but it gets the trends for some coefficient. And so that's this compare the spectrum of this the circular variation after the analysis of this 130 years. So black line is the observation. So overall, our data assimilation underestimates the power of the circular variation. So that's very likely because the model error exists in our system. So brief summary. So I don't think I need to read this out. So I'm happy to take your question. Thank you.
Okay, thank you very much for your excellent talk. Have we got any questions from the floor? Yes, Felix.
Yeah, you showed a comparison between the reference data, like meridional or historic site, where you show the reference, the ENKS, and then the but so the UR and U5 they look very good in terms of amplitude. But what happens when you see them? What's going on? Why is this so different in terms of amplitude?
That's a. So I think so that's probably because they deployed. Well, okay, I haven't really thought about this because in general it gets better results for the toroidal flow from the observation from the ploidal magnetic field. It's get better recovery of the toroidal flow. I guess so for the UC probably we only get good recovery from the toroidal part of the UC, but not the ploidal part of the UC. That's my guess.
Any other comments or questions? No, it's like technical question. I mean, the Kalman filtering assumes you randomly select from the available covariance matrix. Is that what you actually do? So
yes. So we start some free run over many over several magnetic filtering time. So we get this random assembler to start to do this.
Okay. Yeah, and on average, you get something.
Yeah, so the eventual result is given by the average of the assembler.
And how many model runs did you say you had?
The size of assembler or?
Yeah, the size of I mean,
256.
Okay. Any other comments? Okay, in that case, I thank you very much for your talk. And thank all the speakers as well. So we've come to the end of this day's meetings. I don't know, Phil, if you wanted to say anything to wrap up. No, he's saying no. Jason.